思涵，能听见吗？ Hello, everybody. Our conference will start 5 minutes later. So every volunteer, please check your device. Make sure everything is okay. Are you ready? 1 minute left. Ladies and gentlemen, hello, everybody. I'm Jing Xu from Tsinghua University. I'm honored to host this opening seminar. On behalf of the organizing committee, welcome to the first International Forum on 3D optical sensing and application. Until now, the number of registration of this conference is more than 1,200. So it's an amazing number. You can attend our conference by Bilibili and YouTube and Web meeting. Thanks for your participation on this conference. So I noticed the number of audience on Bilibili is now more than 600. So it's a great number. So 3D optical sensing has become one of the hottest and most promising topics and widely used in manufacturing, robotics, and autonomous vehicles. So 3D sensing will change our daily life. Motivated by this promising technique, Purdue University, Tsinghua University, and Nanjing University of Science and Technology organize this international conference. We also appreciate the sponsor from Orbit. So first of all, I'm very happy to introduce our distinguished guest from Purdue and Tsinghua University, Professor Eckhard Glower, Head of School Mechanical Engineering at Purdue University, Professor Jiadao Wang, Chair of Department of Mechanical Engineering at Tsinghua University. Let's welcome Professor Eckhard Glower and Jiadao Wang. Actually, Tsinghua University is the host of this international conference. It's very excited to introduce our first speaker, Professor Jiadao Wang, the Chair of Department of Mechanical Engineering at Tsinghua University. He will give us a speech. So welcome, Professor Jiadao Wang.
Okay, thanks. Respect Professor Eckhard Glower, Head of School of Mechanical Engineering at Purdue University. Distinguished guests, ladies and gentlemen, good morning. Today, we are honored to host the online conference, the first international forum on three-dimensional optical sensing and applications. This conference invited leading scientists and young and promising scholars from the world to share their most exciting achievements and discoveries. This conference provides an open forum to learn most recent leading research findings, exchange new research ideas, and discuss opportunities to work together in the future. The Department of Mechanical Engineering at Tsinghua University is honored to be the host of this forum. I, as the Dean of the department, would like to express my warmest welcome and sincere appreciations to all experts and scholars to join this forum. Department of Mechanical Engineering at Tsinghua University was founded in 1932. It is one of the three earliest engineering departments at Tsinghua University. We have a lot of outstanding alumni, include Qian Wei Chang, Liu Xianzhou, and so on. Besides outstanding achievements in personal training, we have a lot of outstanding accomplishments in scientific research and engineering practices. We have won 25 national awards and 44 provincial and ministerial awards. Now, the Department of Mechanical Engineering at Tsinghua University has three major academic disciplines: mechanical design, manufacturing, and modeling. We have 6 research institutes, including mechanical design, tribology, manufacturing, and others. We have national and provisional key laboratories, such as the State Key Laboratory of Tribology and Seymour National Engineering Center. We have also established the research transformation base, Tianjin Research Institute for Advanced Equipment, and international cooperation base, International Joint Research Laboratory for innovative design and manufacturing of advanced mechanical systems. Our mechanical engineering ranks fourth in QS World University Ranking 2021. In the latest national discipline assessments, we were ranked as A+, the highest level. Now, the Department of Mechanical Engineering has 148 faculty, which is the largest department in Tsinghua University. We have nearly 400 staff, approximately 1,400 undergraduate and graduate students. In our department, there are 5 academicians of the Chinese Academy of Science. 13 faculty won national talent awards, such as the Changjiang Scholars, and so on. 12 faculty won national young talents, and 8 faculty entitled as extraordinary teachers. If you are interested in the mechanical engineering and the relevant disciplines at Tsinghua University, I sincerely invite you to join us. For the 4th International Forum on 3D Optical Sensing and Applications, we have invited world-leading scientists in academia and industry, young promising scholars, and outstanding graduate students to present their work in relevant fields. These outstanding speakers came from 9 different conferences: Australia, China, Germany, Japan, New Zealand, and United Kingdom, the United States of America, Singapore. In the next 2 days, they will share their work with us. It is a great honor for the Department of Mechanical Engineering at Tsinghua University to participate in and host the 4th International Forum on 3D Optical Sensing and Applications. This forum will build a great platform for scholars to freely and openly exchange academic ideas. I sincerely thank the hard work that the organizing committee members put to plan and execute this conference, the outstanding support that numerous students and faculty volunteers provide to make this conference possible. I also would like to express my gratitude to all speakers for the time you put to prepare your presentations. Finally, I would thank all conference attendees for your interest in participating in this conference. I wholeheartedly wish the great success of the 4th International Forum on 3D Optical Sensing and Applications. I wish you all safe and healthy in such extraordinary times. Please enjoy this conference. Thank you.
Okay. Thank you, Professor Wang. Thank you for your speech. So we appreciate your support of our conference. And Purdue University is another organizer. So now let me introduce the second speaker, Professor Eckhard Gruer, the head of the School of Mechanical Engineering at Purdue University. Welcome, Professor Gruer.
Hey, somebody need to unmute me. I think I'm okay now. Right? I think, can you hear me? Hey, welcome from Purdue University. Professor Wang, my esteemed colleague from Tsinghua, I welcome you, esteemed participants of this conference. It's a great pleasure for me to give some welcoming remarks today from Purdue University. If we can go to the second slide, please. I don't know who is advancing my slides, yeah. So here are some fast facts about Purdue University. We are located in the heartland of America in Indiana, in West Lafayette. And Purdue was established in 1869. We just celebrated our 150th anniversary a year ago. We currently have approximately 43,000 students on the West Lafayette campus, but we're also operating several satellite campuses around the state of Indiana. The total enrollment in Purdue is approximately 60, or it's over 60,000 students. We are in engineering. The College of Engineering is number 9 in the USA, as ranked by US News and World Report. So we're a top 10 engineering program. And we are the birthplace of the first Women in Engineering program, as well as the National Society of Black Engineers. So you see, somehow I lost my connection right now. I'm not certain if you can still see my presentation. I will bring it up. Okay, can you go back one more slide, please? Yeah. So overall, we have close to 90,000 engineering alumni worldwide, and we have by far the most astronauts that have received a bachelor or a degree from Purdue than any other university in the US. We actually have 24 astronauts that graduated from Purdue, including a couple from the School of Mechanical Engineering. This is Jerry Ross and Scott Tingle. Let's go to the next slide, please. Specifically about the School of Mechanical Engineering, which I had the great pleasure of chairing since July 1st of 2019. So I'm just 1.5 or a little over 1 year on the job in my third semester. We currently have close to 1,500 undergraduate students and close to 750 graduate students. With these numbers, we are one of the largest departments, mechanical engineering departments in the US. We also have 90 tenure track faculty. We have, in addition, some research faculty and some continuing lecturers and research and other staff to run the school. The total number of faculty and staff in the school is roughly 150. We have world-class research facility. In particularly, we have the largest academic propulsion lab in the world. These are the Maurice Zucrow labs. We have the largest academic HVAC&R lab in the world. This is the Ray W. Herrick labs. The Herrick labs hosting biannual conferences in the field of compressors, HVAC&R systems, and also high-performance buildings. Many people from China, as well as from other places of the world, attend. We have over 800 attendees with representing more than 30 countries. So we're well known for these activities. We also have a fluid power hydraulics lab that is well known throughout the world called the Maha Labs. If you can go to the next slide, please. This gives you an overview of the School of Mechanical Engineering and the various activities that we are pursuing. This is something that we just recently generated and rolled out this summer. In the center, on the center circle, you see 7 what we call fundamental academic areas where our faculty reside, and then on the circumference, on the outer circle, where you're seeing the many different application areas where we're conducting research. So from the fundamental perspectives, we're covering aspects like solid mechanics, system measurements and controls, classical fields of thermodynamics, heat and mass transfer, and fluid mechanics, and dynamics and vibration, and then also do various forms of engineering and design work. But on the outer circle, you do see that we work in acoustics and noise controls, advanced materials, and biomedical application, quite a lot of combustion application, computational engineering. I mentioned the high-performance buildings and the HVAC in our world. We're working on human-machine interactions, how the human interacts with machinery. We have a significant effort in transportation, and this includes transportation from car to trucks to aircrafts. We are working in sustainable energy, robotics, and autonomous vehicles or systems, I should say. Autonomous systems is a big area for us. Propulsion, which goes into airplanes, but also into rocket propulsion and into energetic materials. We're having application areas of particles and powders, in particular towards the pharmaceutical industry and similar application. We're working in micro and nanotechnology, and we are extremely well known for our manufacturing activities, including convergent manufacturing, like 3D printing, and other activities in that field. You could go to the next slide, please. We
Hi. Professor Gloria, are you online? Okay, it seems some problem with the network. Professor Zhang, Professor Song Zhang. Can you open your mic?
Yeah, look like he's lost his connection.
So we wait. Hold on, something.
Yeah. Let me try to send him a message, phone message.
Okay, hold on, please.
Can we unmute him? He just got in.
Okay.
Hey, Song, I just got you back. Can you hear me?
Yeah, now we can, yeah.
All right. So I'm sorry about the technical difficulties. So where did you lose me?
No, just this on this slide.
Did you hear me saying that the ME program is the number
No.
4 mechanical engineering program among public land grant universities in the United States? That was the last comment I made. So maybe we can move on to the next slide.
Okay.
And this is really where you can learn more about our program in general. So again, it's a great pleasure to be here tonight with you. For those who are in China, of course, it's a Saturday morning. I wish you a very successful conference, and I'm sorry about some of the technical difficulties that we're experiencing. Right, we're all working from home. So, but wish you nothing but the best for your conference. Thank you very much.
Okay, thank you. Thank you, Grover. So thank you for speaking. So we appreciate for your attendance and support. So next stage, we will take a group photo. So it will take a couple minutes. So could you open your camera? So it's on the bottom of the Volvo meeting. Professor Zhang, can you show the instruction?
Okay, yeah.
Okay. Okay, I think everybody have. Zihen, are you ready? Zihen, are you ready? So you will be responsible for the taking photo, okay? Professor Zhang, could you stop to share your screen?
Okay. Let me try to.
Yeah, stop sharing your screen.
Oh, okay.
Yeah.
Okay.
Okay, everybody is ready? Zihen, you can take photo right now. Okay. Thank you. So you can close your camera right now. So in this case, we can keep the live streaming is more smoothly. Okay, thanks for your cooperation. So this is our first international forum. So I'm really happy to invite the third speaker, Professor Song Zhang from Purdue University. He is one of the founders of this international forum. So Professor Zhang will introduce the motivation of our international conference. Welcome, Professor Zhang.
Okay, thank you, Professor Xu, and for introduction, and thanks Professor Wang and Professor Guo for spending time with us today and giving your wishes and introduction to Purdue and Tsinghua. So good morning, good afternoon, or good evening, depending on where you are. So it's my distinguished honor to co-organize this first forum with Professor Jing Xu from Tsinghua University, Professor Cao Zuo and Si Jiefeng from Nanjing University of Science and Technology. Professor Xu, Professor Zuo, and Professor Feng, they actually did the hard work, and I'm here to take credit for them. So it's my distinguished honor to introduce this forum. First, I would like to share with everyone our motivations to create this forum, and then I will give a brief overview of this conference. So academic conferences are places for scientists and engineers to discuss and share ideas, to dissemble research findings, and to build networks. They are also the places for students to learn from the best. There are hundreds of, if not thousands of academic conferences happening every year. We love conferences because we travel to nice places, learn local cultures, exchange ideas with peers, make friends, and most importantly, to let our peers know our work and hopefully build our own reputation at a certain stage. So there is a special group of scholars in academia. They are very young. They are recent graduate students or ongoing graduate students. They have creative ideas, ample energies, and unstoppable patience to explore and pursue their dreams. To a great extent, they are the group of people who drive the academia community forward. So over the years, what I found, and some of you may agree, that most academic conferences are too expensive to attend. And they are so expensive so that we cannot attend conferences as frequently as we wish to. We know some scientists have ideas, but these brilliant young people are not always well recognized by the community. They do not have the fame, at least yet, to be invited to attend a conference for free. They were often not given enough opportunities to share their breakthrough ideas beyond the publications. Many of them are frustrated for not being given opportunities. These frustrations sometimes hinder their scientific discoveries and could completely end their dream of pursuing academic happiness. Last year, Professor Xu and I discussed our own struggles and frustrations and thought it could be a good idea for our community if we organize a small forum for young scholars to share and enjoy. Our original plan was to have a much smaller in-person meeting over a 2-day weekend this past summer, of course. In last December, Professor Xu and I met Dr. Howard Huang, who is the CEO and co-founder of OBEC. He graciously agreed to provide all necessary funds for this first event because he is, has great passion for education and has genuine desire to help our 3D community. We are so thankful for his support. Then, of course, we know that COVID pandemic came. We had to change our form from in-person to be online. This social crisis actually benefits our effort because we now can have an opportunity to reach a lot more audience by holding this forum virtually. As of last night, we have over 1,200 people registered. I just look at this Bilibili. Right now, have over 3,500 people attending this opening ceremony right now. We hope that this forum will create opportunities for all of us to share and learn, for us to grow and thrive, and most important, to enjoy and have fun. So learning from the best in the field is the best way to start. As such, we were so honored to invite 4 leading speakers who kindly agreed to give plenary talks. They each have a splendid career in their profession. Professor George Starcis, a renowned professor in mechanical engineering, will give his talk on machine learning and imaging. So this is basically between AI and sensing. Professor Gaza Notani from Technical University Umendao will give a talk about 3D imaging, especially multimodal 3D imaging. This real-time capability offers numerous opportunities for practical applications. We create technology to generate 3D data. So this 3D information must be trusted to do something good. So Professor Richard Leach, he will talk about his perspective on trustless 3D surface data, especially in the manufacturing field. So nothing could happen, of course, without making 3D sensor to the real world. As one of the front runners in commercial world, OBEC is the second largest 3D manufacturer in the world, just behind Apple. So the man who created and leads OBEC right now, Dr. Howard Huang, will share what his company has accomplished in the last 7 years, his personal journey, and his perspective about the future of the 3D world. We have invited 16 keynote speakers from the world, so they will present the, they are rising stars and they are very young to share their outstanding research discovery with us over the next 2 days. So we reached out to 24 leaders from the world and asked them to recommend their best graduate students to present at this forum. And this is our future. This is our future. So in total, we have 44 speakers from different countries, 9 different countries, 44 different research labs. We very much looking forward to their talks today and tomorrow. So this conference would not happen without these outstanding volunteers. They worked extremely hard to make this conference a reality. They had to overcome the time difference challenges to seamlessly work together to solve technical problems. They had to learn how to provide effective guidance to all speakers. They sacrificed their own free time and often their own research for all of us. It was their hard work and sacrifices to give us opportunity to be on this virtual stage to show off stage to learn and enjoy. I, on behalf of the organizing committee, would like to express our gratitude to their outstanding support for our forum. Thank you all. Thank you all and for your time, and I hope you enjoyed the conference and welcome.
Okay, thank you, Professor Zhang. So thank you for your introduction. So this international conference provided the communication platform for the scholar, especially the young scientists. So now we will go to another stage. So now let us start our first planned talk today. I'm very pleased to briefly introduce the Professor Georgia Balabas-Talis. So Georgia Balabas-Talis received his diploma in electrical and computer engineering in 1993 from National Technical University of Athens, and the master and PhD degree in electrical engineering in 1994 and 1997, respectively. So from the California Institute of Technology. So after postdoctoral work at the University of Illinois at the Urbana-Champaign, he joined the faculty at MIT in 1999, where he is now professor of the mechanical engineering. He has worked or held visiting appointment at Harvard University, the Singapore MIT Alliance for Research and Technology Center, and the National University of Singapore, and the University of Michigan and Shanghai Jiao Tong University of Joint Institute in Shanghai, People's Republic of China. His research interests are in machine learning and optimization for computational imaging and inverse problems, and optical system design, including artificial optical materials and interface. He is a member of the Society for Photo Instrumentation Engineering and the Institute of Electronical and Electronic Engineering, and the American Society of Mechanical Engineering. In 2010, he was elected a Fellow of the Optical Society of America. His topic is on the use of deep learning for computational imaging. I think this is a very interesting and promising topic. So welcome, Professor George Balabas-Talis. Okay.
Thank you. Can you hear me?
Yeah.
Okay, very good. I will start my presentation now.
Good morning. My name is George Barbastathis. Today I will talk about the use of deep learning for computational imaging. I would like to thank the organizers of this conference for inviting me to give this tutorial, my current and former research group members who contributed to this work, and our sponsors. I would like to make a distinction between computational imaging, as I use it in this work, and the term computer vision by using this slide. In computer vision, traditionally, the image that is presented on a digital camera is considered to be perfect or close to perfect. And the job of the algorithm is to interpret this image. For example, here, the algorithm would conclude that what is shown is a pear with balls. Computational imaging, on the other hand, the image that appears on the digital camera is not considered to be perfect. In fact, here you see an example where the image is very noisy. It includes diffraction as well as Poisson shot noise effect. And the job of the algorithm is to reveal the content of the image despite the noisiness of the physical system. So because of that, the use of computational imaging is very heavily influenced by physics, whereas in traditional computer vision, typically physics is not necessary for the job of the algorithm. And today I will, of course, be talking about computational imaging in particular. The use of physics in machine learning is a very rapidly growing field. It has been since the beginning because much of the original machine learning work was done by physicists who used inspiration and analogies from physics, even in the earliest algorithms. And of course, physics itself is rife with situations where physical laws or constitutive relationships relating to physical laws are not perfectly known. And recently, we have begun, as a community, we have begun to discover ways that machine learning can augment these less easy, less straightforward to develop aspects of physics. In particular, in this talk, the type of physics, of course, is optical imaging, where we have a physical system, such as a microscope or telescope, forming an intensity image on a digital camera. We call this a raw image. The object of the imaging system is F. This is what we want to reconstruct. And the optical forward operator is H, which allows us to transform the physical object F into the raw intensity image G. And what I'll be talking about is various ways that we can take this intensity image G and then through the use of a learning algorithm such as a neural network to recover a high quality estimate F hat of the original object. The use, as I mentioned, the use of physics in machine learning or machine learning in physics has experienced explosive growth in the last few years. I will simply show a few examples of papers that are actually from different fields outside optics, just to illustrate how successful this has been. This has been from a 2017 paper from the University of Washington, where the authors showed how to use what we call compressive algorithms or sparsity-based algorithms to discover coefficients of partial differential equations, sometimes successfully and sometimes not very successfully. Then there is work from a group at Brown University, also using neural networks this time with a clever split of the training loss function in two terms, one of them coming from the physical model and the other coming from the data, also to discover coefficients of partial differential equations. And this group has published a lot. This is one of the earlier samples of their work. And also another paper from Peking University, where they also similarly discovered the nonlinear differential equation coefficients, but using a different approach than the Brown group. And these are early pieces of work. It is impossible here to review everything that has been done. I would just like to point out that everything in physics is described by PDEs. And of course, the one that is particularly relevant to our community is the Fresnel-Schrödinger equation. And it is the basis of most of the work I will be talking about today. And what makes our work perhaps different than many other ongoing efforts in the community is that we deal with inverse problems, as I will describe in a minute. So what I will say then is the origins of how these algorithms came to be used in computational imaging. I will say a few things about what actually the algorithms learn, if for no other reason to convince you that these are not simply black boxes. We actually come to understand quite a bit about what is happening inside the algorithm and to explain its successes and failures. And then I will tell you a few more things about how the algorithms are trained, mostly with respect to the training loss function and the frequency, the spatial frequency content of the objects that are to be learned. So inverse problems originate from imaging systems. I showed this equation before. G is the raw image, F is the unknown object, and H is the model of the optical system. I will be talking a lot about free space propagation, in which case the forward operator is simply the Fresnel-Schrödinger convolution integral, or you can write it as a partial differential equation. To remind everybody, the easy solution taking the inverse does not work. And that is because H, not only in free space propagation, but it turns out in every optical system, H is ill-posed, meaning that its inverse is sensitive to noise. And often worse, it is singular, meaning that, that it is undersampled or nonlinear and has no unique solution. So how can we deal with this type of difficult problems? The original idea is traced back to two mathematicians, Norbert Wiener in the early 20th century and Andrei Tikhonov in the mid-20th century. What the two proposed in work that was heavily influenced by each other's papers is the solution of these inverse problems through an optimization functional. The functional contains two terms, as you can see here. One of them is called the fitness term because it measures the quadratic error between the prediction of the inverse problem solution and the physical model. That is how well our prediction matches the raw image. So this is the term G minus HF squared. And the second term is the so-called regularizer, which expresses prior information about the problem. If the formulation is expressed correctly, then typically the behavior of this function is shown in this cartoon plot, where it has a single minimum and the two slopes away from the minimum occur either because we're violating the physics, meaning the fitness term, or because we may be violating the prior. And of course, the solution, the optimum, is kind of a happy compromise between the two types of violations. This is ideal. In reality, the algorithm may have multiple minima and so on, but I will not go into too many details of these problems. Let me also say that this type of formulation has been widely used in a lot of problems, especially super resolution, phase retrieval, and tomography that we'll be talking about here as well. And there is also a lot of work on how to shape the forward operator in order to make it better suitable for a particular type of inverse problem. Coded apertures are an example of doing this. And also, even before machine learning became very successful in the 2010s, in the previous decade, in the early 2000s, learning of the prior also was proposed, and it was called dictionary. Another way to understand the way the prior or the regularizer works is as a restriction. So typically the problem in inverse problems is that there is uncertainty due to the noise or due to the nature of the ill-posed forward operator. And the regularizer restricts the presence of the objects, of the possible objects, into a separate subspace. So therefore, when we apply both restrictions, the forward problem that comes with its own uncertainty and a regularizer which restricts the type of objects in a particular way, if we do the job nicely, then we will actually succeed in restricting further the set of possible solutions, and that is, of course, a good thing. And I will be talking later about the Gersper-Saxton-Finnap algorithm. Finnap's contribution in particular was another type of regularizer, which is positivity and finite support in the object. Of course, I mentioned earlier that sparsity was very popular in the early 2000s. The previous decade was very popular as a regularizer for inverse problems. And mathematically, the problem can be solved as an optimization, the way Tikhonov originally proposed it in the mid-20th century. And thus, in the middle of the previous decade, around 2005, proposed that we solve it as a constrained minimization problem. Even before that, the proximal gradient algorithm was invented by many contributions, including Andrew Dubussy in 1997, and it is one way to include both physical propagator H and non-differentiable prior, in particular the L1 metric that expresses sparsity. So that was taken care of by Dubussy's proximal algorithm in the late 1990s. And more recently, starting with a paper from LeCun in 2010, which then evolved over the years with another contribution by Mardani in 2017. The idea was to convert the proximal gradient algorithm. So now, instead of the proximal gradient operator, we use a neural network to express the prior. So the key difference here is that the proximal gradient operator includes a predetermined choice for the prior, in particular sparsity, because it is specifically geared toward L1 type of regularizers. And the LeCun through Mardani developments in the 7 years between the two papers, the prior is being learned, and that is the job of the deep neural network that you see in this diagram over here. Unfortunately, this architecture is known to suffer from the so-called vanishing gradient problem, so it is not easy to train. So what many researchers did in this community is to cascade it. Instead of doing it in a recurrent mode shown here, they unfolded it. And that proved to be easier to train. This is an example from the Mardani paper. The problem they're solving is, they call it super resolution. It is perhaps more fair to call it interpolation problem. You have an image that is undersampled, and you see here the outputs of the 4 neural networks at the successive stages of the cascade. Interestingly, the first stage produces a strongly high-pass filtered image. But then, as you can see in the subsequent stages, the image improves a lot. And then finally, in stage 4, you have a convincingly interpolated image that appears to recover correctly the details that were missing in the original. So this was the state of the art in 2017. And it is important to note that these recurrent and cascaded algorithms, in particular the one by Mardani, which came to be called LISTA, or learning iterative shrinkage and thresholding, the proofs of these algorithms rely on the linearity of the forward operator. So undersampling or interpolation was indeed an appropriate problem for this type of approach. For nonlinear problems, there is no definitive results for how to do this operation. But there are heuristics that we and several other people in the community have used. So, for example, you can use an end-to-end approach where there is no explicit use of the forward operator. One simply starts with a raw image, feeds it into a deep neural network, and then the estimate of the object is produced. Or there's a compromise where you use a physics preprocessor that is denoted as H hat here, and we'll call it approximant. And the job of the approximant is to produce a crude estimate of the object, which is then fed into the deep neural network, and the deep neural network produces the final estimate. I will show several examples of this later, and I will show in particular that when the problem is very noisy and or particularly ill-posed, this estimate f hat 0 is indeed very, very crude. Nevertheless, the neural network algorithm succeeds in producing a decent final estimate f hat. So the first problem I will talk about in this context is phase retrieval. This is, of course, a classical problem in our community, going back to Zernike in the mid-20th century. And it originates from the problem that if you have a pure phase object and you image it at the image plane, the phase of the object is eliminated, because if you take you always have to measure the intensity, and during the intensity measurement operation, that corresponds to modulus square operation in the phasor notation, and that of course will eliminate the phase. So there is different ways to get around this problem. One is to propagate the field by a small amount. This is equivalent to defocus, actually, in an imaging system. And because the propagation operator is convolved over the phase of the object, then after propagation, there will be evidence of the phase in the intensity that we measure, and that can be used in order to estimate the phase f. But of course, this is clearly a nonlinear operation, and from the signal processing point of view, it may be expected to be relatively challenging. I will not dwell on the applications of phase retrieval. There are many of them in astronomy, medicine, biology, and many other fields of science where objects are quasi-transparent. This is one example from work we're doing with several colleagues from MIT and other Singapore universities and research centers for cell manufacturing, and you can see different types of cells, immune cells and stem cells, all quasi-transparent, and using optics in order to reveal the morphology of these cells turns out to have significant implications for their quality and efficacy for the production of personalized medicine. So in our work, at least in our early work, we, instead of using real objects, we preferred to produce custom phase objects. So we used the spatial light modulator. Everybody is familiar with how this works. And the idea was, of course, that with SLM, we know exactly the phase we're trying to recover, and therefore we can quantitatively evaluate the performance of the algorithm. So the modulation of the wavefront is what we input to the SLM, and then the job of the algorithm is to guess what we modulated, and then we can compare the actual modulation to the guess of the algorithm itself. And we use propagation-based methods. So you can see here the phase. If you could visualize it, it would correspond visually to this letter 7, where the yellow parts are large phase, about pi, and the blue parts are a 0 phase delay. And then, of course, you cannot see that because the intensity is uniform on the SLM plane. But after propagation, you see some evidence of the shape of the digit 7, of course, distorted with a lot of diffraction rings due to the propagation. And so the way we solve this problem at the beginning is with what we call an end-to-end approach, where the intensity of this complicated diffraction pattern was input to a deep neural network, and the DNN would produce the estimate of the phase. So we trained it with a few hundreds of examples of known phases and intensities that we produced with the SLM and captured with the camera. And then we tested it with phases that were never shown before, as we say, with disjoint examples from a similar database. The type of neural network that we used was a very celebrated architecture called the UNet that had been originally invented in 2015 for a different application. It was for medical image segmentation. And you can see some results here from the original paper by Ronneberger and collaborators in 2015. But we also used it for phase retrieval. I forgot to say that we labeled the phase retrieval neural network FEN for phase extracting neural network. So UNet was the basis architecture for FEN. And we chose it because, as you can see, the size of the representation of the images decreases progressively as you go deeper into the network, and that is at the waist, at about the middle, halfway through the depth of the network, you have a compressed representation. And since we knew that compressive sensing is a good way to extract, to solve a highly imposed problems, we actually chose this architecture. Interestingly, it is important for this architecture to have so-called skip connections. These are the gray arrows that provide additional connectivity between layers of the input and output size. And both the original 2015 paper and in our work, we discovered that these skip connections are necessary. If you remove them, then the images turn out to be very, very blurry. So the job of these skip connections then is to preserve the high spatial frequency information. I will have more to say about spatial frequencies later in this tutorial. So these are some results of the original FEN paper. What I want to emphasize here is that it had a fairly good, as we say, cross-domain generalization. That means that if you train the network with a particular database, for example, you see here that we trained it with faces, and ImageNet, these are the two training databases, then it is also able to reconstruct phase objects that are produced from a different database. So, for example, Chinese characters, handwritten characters, an alternative phase and natural, face and natural image databases. So this means that the network did not necessarily learn the features of a particular database alone, but it also learned some of the physics that go into image reconstruction in this phase retrieval problem. And we tested this hypothesis by doing additional physics related tests. For example, we know from basic optics that if you use a spoke-like phase target, as shown here, where half the spokes are 0 phase delay and the others are pi, then because of the nature of the chirp-like transfer function of free space, then we know that the intensity image that will be produced after free space propagation will contain phase shifts, where the contrast of the intensity pattern is reversed. And that is, of course, because of the pi phase shift in the transfer function itself. And moreover, if you propagate the field a little further, then these, the rings where these reversals occur will move. And that is because as we propagate the field, the transfer function actually gets squeezed, if you recall the Fresnel propagation curve. So that is, of course, well known from physics. And what we did is we trained FEN, in this case, with natural images, never showed it any spoke patterns. So, so the particular phenomena of what happens when you use a spoke had not been exposed to this training procedure. But nevertheless, the neural network was able to undo this contrast reversal in the intensity images, which suggests that the neural network had embedded some of the physics of the problem. So that was very successful because we showed that with a single neural network, it is possible to learn the physics as well as the priors in order to do a fairly difficult phase retrieval task. So the question is it always possible to do that? So we tested this approach further. We tried to push it to the limits by limiting the number of photons that we made available to the experiment. So this is a similar arrangement here. There is a defocus delta Z in order to produce the propagation based effects of phase onto the intensity. And in addition, we used a variable neutral density filter, essentially an attenuator, which allowed us to reduce the photon flux onto the CCD by as little as 1 photon per pixel. So here I show you a sequence of experiments, numerical reconstructions experiments that we did on physically acquired images from the actual experimental arrangement we had in the lab. So you see here that two sets of experiments, one with 1,000 photons per pixel and one with a single photon per pixel. And then you see three types of reconstruction algorithms. One is the Gertz-per-Saxton FinUp. I show you here one pass of the Gertz-per-Saxton FinUp. It is actually surprisingly good, given that given how noisy the original images were. But actually, it does not improve much more if you were to run it for more iterations. And then I show you results from a single neural network, very similar to the previous architecture that I showed before. And you see that it is also very poor, but in a different way. It yields reconstructions that are very blurry. And that is, of course, because in this very, very noisy case, the network is not capable, through its training procedure, it is not capable of learning both the physics and the regularizer that will be necessary to solve this very difficult inverse problem. So the way we solved this, at least in our first effort a couple of years ago, was to use what we call an approximate. So the approximate here is the third column that you see in this chart, the Gertz-per-Saxton, and one single iteration of the Gertz-per-Saxton. And so now this poor image that the Gertz-per-Saxton produces due to the very noisy input is then fed into the deep neural network. And then, as you can see, the neural network is capable of producing a fairly good quality reconstruction, especially for the 1,000 photons. For the 1 photon, it does show some improvement, but it is still fairly blurry. It has missed some of the high spatial frequency information. So please keep that point in mind. I will come back to it later. I'd like to say a few words about how we train the neural networks. This is a very impartial menu of training metrics. Some of them are familiar: mean square error and mean absolute error, correlation coefficients and variations of the correlation coefficients. And of course, I want to emphasize that in the literature, there is a vast variety of training loss functions, of optimization metrics to train neural networks, which are beside the point of this tutorial, so I will not review them all. The one that I would like to mention is the perceptual loss metric, because it borrows a little from human perception. It was invented by a group at Stanford a few years ago. And the idea is to use two neural networks for training. One of them is DNN1, is the familiar neural network that we use in order to do the inverse problem. And the second neural network is a classification network. It receives as input of it receives as its input the output of the image forming network. This is what we denote as FHAT. And then, of course, the purpose of the second neural network is to produce a classification in the traditional sense of machine vision. And what Johnson and his co-authors proposed is that to train the first network by comparing the intermediate representations that its inputs produce in the second classification neural network. So denote those here as S2, SL, and so on. So these are the outputs of the intermediate layers that whose goal is eventually to produce the classification result in the final layer. So we tried this idea with the noisy inputs for phase retrieval, and we got some encouraging reconstructions. As you can see here, unlike our previous approach, this perceptual loss network was able to retrieve some of the high frequency information, but we also noticed a very strong artifact in the reconstructions that looks like a checkerboard pattern. This artifact had been mentioned in the original paper by Johnson, but it was not very prominent because Johnson's inputs were not very noisy, unlike the examples I'm showing here. So we investigated a little bit deeper, and in particular, we try to compare what happens if we use, for perceptual training, if we use representations for different intermediate layers within the classification neural network, which in this case was the famous VGG16, at least famous at the time. And we looked at the power spectral density of the reconstructions, where this checkerboard artifact becomes evident in a form of peaks, of course, because of the periodicity of the artifact. And we found that depending on the layer within the VGG network that you choose to do the perceptual training, the frequency of these peaks actually halves. It becomes half as you go deeper and deeper into the network. And there's no formal proof of this, but intuitively, this is due to the convolution operators that are used in neural networks, followed by nonlinear operators, typically the so-called ReLU, or rectified linear unit. So it is not totally surprising that this frequency halving happens, but it is detrimental in this case because it carries over in the reconstructions. So the original Johnson paper recommended the ReLU 22 layer to do the perceptual training. Unfortunately, we found that for very noisy inputs, the frequency of the artifacts here is at half the Nyquist frequency, so it is very visible and very annoying. But we also discovered that if we instead use the ReLU 1-2 layer, a few layers earlier, then the frequency of the artifacts is pushed to the Nyquist value, and therefore it does not become, it is not perceived anymore into the reconstructions, and that leads to a significant improvement. So I'd like to say a few things more about this power spectral density. It is a quality that also originates in the work of Wiener, and you can interpret it as a relative popularity of frequencies in the in the statistical class of objects that you're interested in. This is a fairly straightforward implementation of the, interpretation of the so-called Wiener-Khinchin theorem that is standard in signal processing textbooks. So, for example, for natural images, it has been well established in the psychology and visual neuroscience research. It has been well established that both natural images and the visual cortex of the human brain, they process frequencies with a preference to lower frequencies. And that is because the power spectral density has this inverse square power relationship. And that means that the low frequencies are dominant, and that is as it should be when it comes to visual processing and perception. However, when it comes to neural network training, it means that during training, the lower spatial frequencies also become dominant. And now that is kind of like a double whammy. It means that the high frequencies now are suppressed during the training process, and we speculated that this may be one of the reasons why all of the techniques that I showed so far, when it comes to noisy images, they have trouble reconstructing the fine detail, the high spatial frequencies. In the next slide, I will show you some examples of how these power spectral densities look like. So for faces and natural images, very similar to natural images, you can see here evidently the inverse square law. When it comes to other types of databases, of course, the dependency is different. So for example, if you look at integrated circuits as a class of objects, you can see a lot of spikes, which are of course due to the fact that integrated circuits are on a Manhattan geometry and quasi-periodic. So you see a lot of harmonics in power spectral density. Be that as it may, when you train a neural network and you use one of these classes of objects as a prior, the power spectral density will influence both the training process and the performance of the network after training. So my student Mo Deng, in order to address this problem, he devised the two-channel type of processing, where the low and high spatial frequencies are separated at the beginning of training. And the hope of doing that is that the high spatial frequencies in this scheme, they will suffer less due to the fact that they are underrepresented in the various training sets. So you can see the scheme here, we call it learning to synthesize. There is two neural networks. One of them processes the low frequencies and another processes the high frequencies. And at the output of these two networks, you have now two reconstructions for the corresponding frequency bands that is optimized for the corresponding frequency bands. And then the question is how to combine them. And the idea here is to train a third neural network that we call a synthesizer, DNNS, that receives the input from the low frequencies, then does a transformation on it, and then optimizes this transformation such that when you combine it linearly with a high frequency output, it gives you an optimized reconstruction. And what I want to emphasize here is that these three networks that are trained separately with spatially filtered versions of the training examples. The details of how this is done are in our paper. So this is how the scheme works. You saw several plots here. One of them is the ground truth, that is the blue plot, and what you see is the inverse square power law. This was for natural images, this particular example. And then the approximant, which is, as before, it is the Gertz per Saxton algorithm. And you can see the approximant behaves fairly well at low frequencies, even better at intermediate frequencies, and very poorly at low frequencies, not surprisingly. The low frequency output, which turns out to be identical to FEN, is the yellow curve, and as you can see, it deteriorates at high frequencies quite rapidly. And then the DNNH output is purple, which you see now approximate. It is still not perfect at high frequencies, but it is much better than the L network, and it also suffers at low frequencies because, of course, DNNH is trained with high spatially filtered examples. And then finally, S is the output of the synthesizer, which the green curve, which you see is a compromise. It works fairly well at all frequencies, high, low, and intermediate. And finally, as a comparison, you can see here everything that I said so far about phase retrieval. You can see that end-to-end with a noisy input, end-to-end gives you very blurry results. The traditional Gertz per Saxton gives a very noisy output that resembles the true signal but is very, very noisy. And then you can see the three approaches that I mentioned. One is a simple FEN with approximant, and then the approximant with perceptual training optimized to avoid the checkerboard artifact. And then finally, the approximant with learning to synthesize, which visually and quantitatively turns out to give the best result. In the last few minutes, I would like to talk a little bit about the reconstruction of the interior of objects. Another famous and very important ill-posed problem that very often, perhaps a bit confusingly, is called tomography. Traditionally, the term tomography corresponds to a particular class of approximations for the interaction of the electromagnetic field with the object that is appropriate when we use very short wavelengths, for example, X-rays, at which, moreover, the index contrast that the object presents relative to free space is fairly low. If that is the case, then the interaction is well described mathematically by the so-called radon transform, whose, of course, inversion is a classical problem in applied mathematics and is used in imaging biological objects, led to the Nobel Prize in the 1970s. A different class of problems occurs if the interaction between the light and the object is strong, which will happen generally at longer wavelengths, where also the index of refraction produces high contrast between the object and the surroundings. And of course, in these cases, the radon approximation is not valid. One has to do rather more elaborate approximations such as Born series and Feynman diagrams, or perhaps a more straightforward, albeit less rigorous approximation is the so-called beam propagation method that we also used in our work. There's a beautiful example of using learning architecture in order to solve this type of strong scattering tomography problem, and that was by Camilo in 2015 when he was at EPFL in Lausanne, where they noticed that the beam propagation, the structure of the beam propagation algorithm resembles a neural network. And therefore, when you try to solve the inverse problem by a form of inverse gradient, they noticed that this is very similar to the training of a neural network mathematically. So you can see some of the results from their work here. It was very successful at reconstructing fairly simple combinations of highly scattering objects, such as the two dielectric spheres that you see arranged in the most difficult case. They are arranged along the longitudinal axis of the optical system. So inspired by this work and a follow-up paper in 2016 by the same group by Kamilov, we tried to see if we can use a neural network to invert even more complicated, highly scattering objects. So in this case, we used the Kamilov algorithm as an approximant, that is, as a preprocessor. And then the job of the deep neural network is to learn how to take this estimate produced by Kamilov's paper and convert it to a higher quality reconstruction. So in our experiment, we used a physical artifact. We fabricated a glass sample, as I will show on the next slide. And so we used that for testing the network. But to train the network, we used pure simulation. So we had the actual artifact, the physical artifact was never included in the training. We had hundreds of examples of statistically similar artifacts, but never the same, which we used with a combination of the beam propagation method as a physical model to simulate the propagation of the light through those samples, and then to train the neural network this way. What makes this even more challenging is that we used a limited set of angles of illumination for this experiment, going from plus 10 to minus 10 degrees in a total of 23 intensity projections. So here you see the structure of the sample. It consists of four layers of glass, and on top of each glass slide, we fabricated rectangular patterns in agreement with an IC layout that we had available. And of course, these are not functioning integrated circuits. We simply emulated the patterns that you find on the IC layout, and we reproduced them at a scale of approximately 1,000 times bigger in the lateral dimension. So whereas in the IC normally you would have a few tens of nanometers in feature size, here the feature size was in the order of a few tens or hundreds of micrometers. And you can see here the 4 layers of the ground truth. These are we take this as ground truth because this is how the sample was constructed by using optical lithography. And of course, these are large features. They were reproduced by the lithography process with very high fidelity. And then what you see on the right-hand side, first of all, is you see part A is the raw intensity that we record on the camera, which, as you can see, it has evidence of the various 4 layers beneath with a lot of diffraction artifacts. And then you can see the approximant for layer 1 now only. The approximant is, of course, the Kamilov 2016 paper. And you can see that it is not really capable of doing a very good job because this specimen is much more complicated than the simple combinations of spheres that Kamilov's paper demonstrates. Even so, and of course we can reproduce approximants for all 4 layers, not shown here. They're all of equally poor quality, but even so these approximants are very poor. You can see that the final output of the neural network that we constructed produces fairly good fidelity, not perfect, but fairly good. And you can see here in juxtaposition the 4 layers of the ground truth and the reconstructions by the neural network in order to get an idea. As you can see, there are a few errors, a few voxels that are reconstructed incorrectly, but the overall structures appear to be of decent fidelity relative to the truth. I would like to close this tutorial by pointing out again that human vision is of course very powerful and results from a combination of very sophisticated hardware. The human eye is an amazing optical instrument, together with the human brain, which whose a big part of is dealing with processing the images that come from the eye. And of course, it is also well known that the human brain is not really pre-programmed. To a large degree, the human brain is also trained during the early stages of childhood in order to learn how to associate the raw signals that are received by the hardware of the eye to associate them with what we call visual perception. And what our community of computational imaging is perhaps more and more successfully achieving is superhuman vision, achieving things that the normal human vision cannot do. For example, imaging pure phase objects that would appear more or less transparent to the human eye, or the interior of objects, which also, of course, humans cannot do. And what is really exciting in this field is that by use of machine learning algorithms that are trained, of course, in a very different way than the human visual system, we train our algorithms using spatial light modulators or beam propagation simulations and so on and so forth. Nevertheless, we're capable of performing these superhuman vision tasks fairly successfully under challenging circumstances. And I chose to emphasize in this tutorial 2 particular situations. One of them is the challenge comes from very noisy inputs, very low signal levels that lead to images that are dominated by shot noise. And the other example I showed you is highly scattering objects in tomography, where again the limitation is that the strong scattering from the object makes the problem highly imposed and highly nonlinear. So with that, I will end my presentation here, and thank you for your attention.
Thank you, thank you. Thank you, Professor Balaba Starlit. So I think you have done a very, very great work and given a very, very interesting talk. So because of there are lots of people's interest in your topic. So I see the number of audience on Bilibili is more than 4,000. So it's a very, very big number. So actually there are lots of questions, but the time limitation. So I just select a few questions. The first question is about the deep learning. So how do you get the large scale data set for network training? The second the second question is what's the relationship between the network performance and the scale of the data set? Thank you.
Yeah, so we get the data sets from publicly available sources, and then all we have to do for one such example is ImageNet that contains natural images. The other example is MNIST that contains handwritten digits, and there's many others. So all we have to do is display these data sets onto the SLM. And to answer the second question, of course, the more examples we produce, the better the result. Typically, we need to use between a few hundred and maybe 1,000 or 2,000 examples to get the training to perform successfully.
Okay, so another question is, do we need to sample during the reconstruction by the DNA network?
Well, the images are, if I understand the question correctly, the images are always sampled, right? Because the camera, because of the pixels on the camera, or maybe I did not understand the question correctly.
Okay, okay. So the next question is, the reconstruction is a point to point or point to phrase?
I'm sorry, again, I did not understand. Point to point or point to?
Phase or plan?
The reconstruction is also pixel based. So the input to the network is pixels representing intensity on a digital camera, and the output is pixels representing estimates of phase in the object plane.
Okay. So is there any question? Okay. Thank you. Thank you again.
Thank you very much.
Thank you again.
Thank you.
Okay. Thanks, everybody. So the planned talk on this morning will be ended. So the keynote and the invited talk will begin soon. So the keynote talk will still in this room, and the invited talk will move to another room. You can check the information on our website. Okay. See you soon. Bye-bye.
Thank you. Hello, I think we have a 5 minutes break. So we will start our session from 10:05. Yeah, but you are still unmuted.
Hi.
Oh, yeah, that's great.
Sorry, there is some problem with my computer and I just fixed it. Sorry.
It's perfect now.
Okay,
So
can
we
you see
start
my slide?
Yes.
Okay, thank you.
So yeah, we start in 2 minutes time.
Sure, no problem.
Yeah, let's start. Good morning, ladies and gentlemen. Yeah, as Professor Song Zhang said, it depends on where you are. Maybe it is good afternoon or good evening, but welcome back to our first keynote session. It's my honor to chair this session together with Professor Liu. We have 4 excellent talks in this session. The first session will be given by Professor Zhao Huichan. I give a very simple introduction to Professor Zhao. Prof. Zhao is an assistant professor in the Department of Mechanical Engineering at Tsinghua University. She received her bachelor's degree from Tsinghua University in 2012 and a PhD degree from Cornell University in 2017. During 2017 and 2018, she was a postdoc at Harvard University. Her research interests include soft robotics, bio-inspired robotics, smart materials, flexible sensors and actuators, etc. Some of her works are published in Nature, Science, Robotics, and so on. She was listed in 30 under 30 Forbes China in 2018. So we look forward to her very exciting talk. So Professor Zhao, the time is yours, please.
Okay, thank you very much for Professor Qian for the great the introduction in great details, and thanks very much for Professor Xu Jing for inviting me for this talk. Actually, we are colleagues in Department of Mechanical Engineering in Tsinghua University. I joined the department about 2 years ago. To tell the truth, I am not like a researcher in the area of optical sensing, but I did use optical signals to sense some of our very important parameters in software robotics. So today, I'm very happy to share my previous research with all of you, and your question and suggestions are very welcome. So here's my background. I won't duplicate it as Professor Qian already introduced me in great detail. So I would like to first give a brief introduction of the research area that I am working on, which is called software robotics. So when you think of robots, you always think of those like humanoid robots that is made of steel joints and actuated by, for example, the very high power actuators. But our soft actuators is made of soft materials. When we see the definition of soft robotics, we always see that the Young's modulus of the compositional material of soft robotics is much lower than that of the common materials for robotics, like steel, like the very hard plastic. We use, for example, rubbers, fabrics, and other human skin level material to make those kind of robots. So here is a comparison of the traditional or the more popular robots that in most people's mind and the software robotics that I am working on. So when you think of the traditional robots, it is usually driven by servo motor plus a reducer, and the sensing is always accomplished by some like force and torque sensor, etc. And its basic foundation, its math foundation is based on kinematics and dynamics of rigid body. So, but for software robotics, it is very different. We always use artificial muscles to actuate robots, and we use artificial skin to sense, to communicate with the environment and other robots. And the fundamental for this area is the mechanics and the dynamics of elastomers and the continuum. So it's very different. And another point of view is we got our inspiration from, for example, the invertebrate animals like octopus in this slide. Here are some very recent advances in the area of software robotics. Like the first one is simulating robot that can mimic all kinds of shape just by patterning fabrics on elastomers. And the second one on the right up corner is a Stanford software robot that can grow. It is inspired not by animals, but by plants. And the rest two, one of them is the world first completely soft robot, as all of its components is made of soft robotics. For example, its battery, its control system is all made with softer materials. And the last one is one of the fattest soft robot in the world. Okay, so here's my research area. My research mainly focuses on 4 aspects. And for example, and my group members are making those kind of soft actuators for driving soft robots, and also soft sensing to sense how our robots are moving, and the soft robotic control and novel fabrication techniques for soft robots. And today, after that, we would apply all those fundamental technologies to some applications. For example, bio-inspired robotics, medical applications like rehabilitation glove, or some prosthetics to help the disabled people. Today, I'm going to share two topics with you. One is soft sensing and the other is soft actuation. In particular, soft sensing is very related to optical, so I think it's a good topic here. So why we want to do soft sensing for soft robots? As you can see, soft robots exhibit very, very large strain when they are performing. For example, they have very high stretchability of the body materials. So there is a challenge that if you think of some other normal sensors like the strain gauges, IMUs, load cells, and others, all of them are relatively very rigid. They can hardly be incorporated into soft robotics, which will have very large strain while functioning. So we have to find a stretchable sensor so that they can easily incorporate it into soft robots and sense the large deformation of it. Previously, researchers use electrical signals to sense the very large signal. For example, one way they do it is to incorporate those kind of conductive particles in elastomers so that this elastomer is conductive and stretchable at the same time. And then they use the resistance or capacitance signal to sense how much strain the material is experiencing. But there are some problems with this technology, because those particles incorporated in elastomers will experience some irreversible deformation during the stretching. So the signal has a lot of hysteresis and is of low signal to noise ratio. So we all know that optical signals is a great kind of signal for sensing. So can we make a stretchable optical sensor that we can still use optical signal, but it is made of softer materials? And that is my work. So what we did is we made waveguide sensors by ourselves. So I think all of you know what is a waveguide. It has a refractive index. It has a high refractive index core material and a low refractive index cladding material, so that when light propagates along this waveguide, it has total reflection along the surfaces between the core and the cladding, so that the signal can transfer through a very long like contour, and it can also turn. So for example, in our case, we used a polyurethane material as a core and a silicone material as a cladding. They have a refractive index difference of about 0.04, and the light can propagate it very effectively. And the good thing or different thing of this waveguide compared with the previous waveguide or optical fiber is that all the material is made of stretchable, highly stretchable material, so that this sensor can also be stretchable. And also it contains the key advantages of most optical sensors, like it has very high signal to noise ratio, and it has very high repeatability. Here is a video showing the performance of our sensor. In this case, we are stretching this our made stretchable waveguide sensors, and at the same time, we're recording its signal. So you can see that its strain is quite linear and quite accurately perceived by this optical fiber. This is one of the demonstrations, so that we can use these sensors as a strain sensor, just like a strain gauge, but it is of very high stretchability and signal to noise ratio. And this one is to showing that it is of very high repeatability. No matter how many times, maybe hundreds or thousands or even hundreds of thousands of times you stretch it, you will always get the exactly same material. There's no hysteresis and creep. Okay, so here is another demonstration showing that this sensor can not only be used as a strain sensor, but also as a, for example, a pressure sensor. Here is a demonstration that I am pressing this sensor using different kind of small plate, and we can get this signal with very sensitive response. So it can be used as a force sensor in robotics. So until now, I think you're very curious of how we are going to use it in soft robotics. Here's what we do. So we incorporated 15 of those optical fibers into a soft prosthetic hand. This prosthetic hand is made of a 3D printed palm, which is a solid one, which is a non-moving one, and also with 5 soft fingers. All these fingers can bend towards one direction so that it is more like a human's hand function. So what we did is we incorporate those sensors into these soft hands so that we like innervated it. We give it a feeling of sense. Here's a demonstration of this robotic hand. Like most soft robotic hand, it is very dexterous and powerful. It can grasp shapes with all kinds of, it can grasp objects with all kinds of shapes and stiffness. Some other interesting thing is, for example, when humans is interacting it know it because it has sensors in it at its tip. Here's also a demonstration showing this robotic hand scanning 3 tomatoes, and then, like our humans, press each one very gently so that it know what is the stiffness of this tomato, so that it can pick up the white one. There is another demonstration showing that it goes through a surface and it can reconstruct the surface shape. Here is a construction result. You can see that it is a very high resolution. It can sense the very small rough surface and reconstruct the shape of it, like the very last one. So even though this hand is still, its sensation capability is still very far away from a human's hand, it gives us a great opportunity to use optical signals to give robots a kind of a sense. So this paper was published on the first issue of Science Robotics in 2016. Later, we collaborated with Professor Cindy Harnett in University of Louisville, and she used this kind of optical fibers as a sewing material so that she can put this sensor on humans' clothes. And then, for example, when you are doing sports, you can use this kind of sensor to sense your motions. So this is one of the work. So the second topic that I want to share with you is a little bit far from optical sensing, but it's also very interesting. It's called the soft actuation. So the goal of the motivation of this research is for our automobiles, for our humans, for our industrial robots, we all have very powerful actuators, like the engines, our muscles, and the motors. But what is the actuator for next generation robots? So recent years, there are many kind of new materials like chip memory alloys, piezoelectronics, electromotors, and artificial muscles, all these kinds. Among them, one of them is very interesting. It is called dielectric elastomer actuators. This one is of very high activation frequency and very high energy density. So can we work on this kind of soft sensors to be as the muscles for next generation robot? This is a basic foundation for dielectric elastomer actuators. So basically, it is a compliant capacitor. When the electric field is applied on this material, it can expand. We can use this motion to do work. So this is a brief history of this kind of materials, which I will skip. As you know that it was found about 300 years ago, but only in recent 20 years, it started to attract researchers' attention. So there are many pros and cons for this material. It has very fast responses and large strengths, and controlled by directly electricity, not like many other smart materials that are actuated by heat or optics, which is hard to get. Electricity is with us every day. But there are also some cons. The high driving voltage of this material. You usually use like tens of kilovolts to drive this material. And it is not very easy to use for a long time. So our goal is to reduce the voltage and increase its life cycle. So what we did is we come up with a new kind of fabrication techniques for this material. We make each layer of this material very, very thin. and laminate them together and form this kind of very small actuator. And here is a scalable manufacturing method for this material, which I will not go into too much details. And we established the mechanical model for this material, as well as do some simulation to predict how much displacement and how much force it can generate. We characterized this soft actuator, and here is a dynamic model, which I will also skip. Let's go to its demonstration. So this is a material. It can vibrate at a very, very high frequency, like 500 hertz. So what can we use for it? There is one of the application. We used all of these actuators and made it into a wearable device and worn on a human's arm, so that this device can transfer information, just like our visual information and our audio information. But in here, we use haptic signal to sense, to give people a feeling of sense. So for example, if you and your family are very far away from each other and your family wants to pet you, she or he cannot do it because you are in different places. But if you wear this machine, you can feel a sense of being touched remotely. So this can be a potential communication device in the future. So we also characterized its thermal properties to make sure it is not very hot, so that it might cause harm to humans. And we did a lot of human tests on how much, if people can sense this kind of materials, and the results are quite promising. People wear this machine can sense the different positions and different directions of actuation of this device. So in the future, we might expand it into a larger area so that it can give people more amount of knowledge and information. So another very interesting application for this one is we used it as an artificial muscle for a robotic bee. This is a robotic bee or robotic fly. And we make these actuators even smaller and incorporated into a mechanical design of a robotic flying machine. And this machine can achieve human-like, not a human-like, sorry, animal-like flying, flapping flying. Here is a mechanical design of it. And here is a video showing that, showing at low speed of when this actuator is moving, how is the wings flapping. And using this small machine, we achieved the first flying of this kind of artificial muscle-driven flying machine. And it can fly steadily in air for 20 seconds. Okay, so here is what I want to show with you today. Today, I covered the soft activation, the soft sensing topic. And in the future, if you had a chance, I would be very honored to share with you about the other two topics that I was also working on. So here is thank my PhD lab at Cornell and my postdoc lab at Harvard and my current lab at Tsinghua University. Thank you for listening and welcome for questions.
Thank you, Professor Zhao. I think we have plenty of time for Q&A. We have about 10 minutes for Q&A. So do you have any questions? Okay, let me start the first question. So for the optical fiber, what is the material you used? I think I missed that point. I think the material is pretty interesting. It can stretch so long.
Yeah, so for the core material, we are using a material called the polyurethane rubber. It is very stretchable as well as very translucent, transparent. So it can propagate light, and it is also very stretchable. I think this is a very commonly used material, like in our life, some foams are made of this material. And the cladding material is also very common. It is called the silicone rubber, or PDMS. It is a material also with high stretchability, but opaque. It cannot transfer light.
Okay, so what is the size of the core and the cladding?
Size or that's a good question. So I was communicating with one of my friends who is working on optical fiber. He's an expert in optical fiber. He doesn't think that what I was making is a waveguide because our core has a dimension of 1 millimeter. He told me that there are 1,000 modes in this optical fiber. So yeah, and I agree.
So this is a more properly, actually, it is geometrical optics rather than wave propagation.
Yeah, that's true. But yeah, so for our modeling for this optical fiber, we obviously use some geometric modeling of light rather than the wave side of it. But I think making it shrink its size would cause some more interesting characteristics, which we are trying right now. We are shrinking the size, but it caused some problems of fabrication. So we are still working on these very challenging problems.
Okay, so the materials, you can buy them from the market?
Which one?
The core material and the cladding material.
Mm-hmm.
You mentioned
yeah, that's true.
You said they are pretty common now, so you can easily get it from the market.
Yeah, we usually buy the pre-elastomer, which means when we get the material, it's still liquid, and then we synthesize it so that it becomes a solidified elastomer. The process is not very complex. Yeah.
Okay. Thank you. So
thank you.
Yeah, I have a couple questions. So
sure.
Yeah. Okay. Yeah. Please.
Yeah, so I think your work is very, very exciting. So I have like, all these sensor, you like the fiber sensor, also the second part of the sensor you developed, right? So do you fabricate everything by yourself in your lab, or you ask some company to do it for you?
Actually, most of the work was done in the lab. In the future, we might, yeah. But it's not that complex, and the fabrication technique is one of the innovations. It's one of the key innovative part of our work, because
yeah, that's
in
what
theory,
I feel.
yeah, in theory, it is not very complex. You just make a cladding and a core, and then it becomes optical fiber and change it with softer materials. But in reality, it's very hard. The surface roughness between the core and the cladding are very, very tricky. If it become a little bit more rougher, then none of the light is transferred, and we lost all the sensor. So such problems need to be solved.
Yeah, that is very difficult to do in the lab.
Yeah,
so
sure.
For the second, like the use rotary manufacturing process, that is also made in your lab as well.
You mean the actuator, the small actuator?
Yeah.
It is also made in the lab, but we are not making all of them by hand. We have some machines like a spin coater, like a film applicator to help us make a very high quality films. And we use some other machines to make the electrodes, etc.
Yeah, I was wondering whether, we Purdue, we just hired one faculty from Harvard, whether you work in the same lab. So his name, is Alex?
Who is? Oh yeah, Alex. Yeah. Alex,
okay, that makes sense.
Yeah, we were from the same, so I was supervised by two advisors, and so I'm in two labs, and he is also in two labs, but we have one overlapped one.
I see, because I feel like he did a lot of like when he presented his work, right? He did a lot of like work on the fabrication, how we actually do that with 3D printing like techniques. That that is really difficult to do.
He is working on 3D printing technology to do the DA, and I was on more like another like laminating method to making the DA. Yeah.
So for the flapping wing, like micro robot, right? You did. So can you control this like flapping wing? This one. Can you control this like the flapping, the wind speed very well?
This is the wind speed. The wing is flapping at about 280 hertz. And yes, we need to control this frequency so that its lift can be adjusted.
Okay, so you can control it precisely, right?
Yeah, you can, because this material is rather linear, so that you can control it quite well. So I skipped a lot, but this is just to prove that it has very linear output of force and displacement, so that we can control it using our signals.
I see. Look like, you talk about like 1000 voltage, right? To control this,
That's
like
that's very low voltage in this area.
What kind of current do you use?
The current is very small. It's about a few milliamps, 1 milliamps or to 5 milliamps.
Okay.
Yeah.
So in other words, this will not
dangerous.
cause you do not cause some harm to people, right? If they
you will feel a very a very short moment of uncomfort, but it's very short. It's just like a millisecond. Yeah.
Okay, that's great talk. Thanks.
Thank you, Professor Zhang.
Okay, we still have a few minutes, so any questions from the audience? By the way, from the Bilibili, I saw one comment saying that you are 好厉害, so you are
Thank
great.
you. Thanks.
Okay, so another thing is that actually you are our first keynote speaker, and you are a female scientist. So do you have anything to share with our, say, female students, female young researchers? You know, you are in Tsinghua University, or such a well-known university, and you have done great job. So do you have anything to share with others?
Actually, this is a very difficult question. I don't want to say anything that that I'm not very prepared, because this is a high pressure problem. To tell the truth, I think a female scientist will experience some hard time compared with its male counterparts. For example, you will have to plan your life as well as your career at the same time. But I think in terms of intelligence, in terms of devotion, all these parts, females are as great as males. So if you have a dream to work on something, then I would very highly encourage you to devote your time to it. And you will say that you will get more than others if you can achieve it. I'm sorry. This is what I think. Actually, I have several female students in my group, and I think all of them are doing really, really great work. And female students, if you're interested in my research, you're welcome to contact me, and we can talk about some potential positions. Yeah.
Okay. 女神能顶半边天. Thank you very much. So we indeed have some questions coming in, but I think the time is not allowed. So for the audience, if you want to ask questions, please ask as early as possible. So thank you again for your great talk. We move on to the next speaker, Dr. Daoling Ma. So Dr. Ma, please share your slide and prepare to make your presentation. So in the meantime, I give a simple introduction of Dr. Ma. Dr. Daoling Ma is a postdoc researcher in robotics manipulation at M-Cube Lab in the Department of Mechanical Engineering at MIT. Dr. Ma received both bachelor and PhD degrees from Peking University. His research focuses on contact modeling, tactile sensing, and robotic manipulation. I think there will be some overlap with our Professor Zhao. So Prof. Ma, it's your time. Yes, great. We can see the slide.
Okay, can you hear me?
Yes.
Yeah. Good morning, everyone. Thank you, Professor Xu, and for inviting me here. My name is Dao Ma. I'm postdoc researcher at MIT right now. I'm advised by Professor Alberto Rodriguez. Today, I'm going to present our recent research about high-resolution tactile sensing and perception for the purpose of robotic manipulation. If you wonder why tactile sensing is related to this forum, it's because our tactile sensor is a vision-based tactile sensor. So the aging population and the shortage of laborers have raised high expectations for the robotic automation. But for decades, the robots have been doing the work on the left side. The environment is highly structured, and the precision of everything is very high, and the solutions are mostly open loop. However, in the future, the robots are expected to tackle challenges from different scenarios. For example, in the warehouse, millions of different objects are stored inaccurately, and they need to be found, to be picked up, and to be packed and delivered. For example,
excuse me, Dr. Ma. Can
yes?
you play your slide? Then we can see a larger screen. Seems like
you are watching. Sorry,
the raw version? Yeah.
We are watching a presentable. Yeah.
Let me try again. Sometimes I encountered this problem. Let's share. I'm playing, but because I have,
I see.
maybe it's because I have two screens. Let's see. How about now?
I think it should be okay.
Is this the correct one?
Yes, yes.
Okay, great.
Yes, thank you.
Thank you. For example, in the kitchen, where the dishes and forks are piled up like randomly, they need to be cleaned. And very importantly, in the factories, different parts need to be assembled carefully. And even in the outer space where the in-orbit maintenance needs to be carried out, and we expect robots to perform in such scenarios. However, these tasks are very hard to be automated, mostly because of the tedious interactions that is involved in these tasks. And reactive manipulation is critical for the solutions. The question is, how can we make the robots reactive by closing the control loop? To close the loop, sensing and perception is the key. For example, in 2017, we participate in the Amazon Robotics Challenge. Our robotic system can pick the different and novel objects from the bin and place them in the specific places. The core enabling technology behind this is the visual perception, and the core behind this visual perception on the hardware side is the RGB camera on the hardware side and the AI algorithm on the perception side. However, in the tasks that we mentioned previously, where the interaction is very important, only visual perception is not enough, because the cameras usually suffer from occlusion, especially when the objects are close to each other. And what's most important is that the visual perception cannot reflect the interaction between objects directly. Just like the human workers in the factory, they need the combination of hand and eye to accomplish their tasks. So in the future robotics, we need the robots to have the capability of tactile sensing. So then today I'm going to focus. So today my talk will focus on the tactile sensing. So my presentation today will have about two parts. The first part is about the tactile sensing, which is on the hardware design and how we can extract the low-level tactile information from the tactile sensor. And the second part is the contact perception, which is how we can consume the tactile information in the robotic manipulation, which is about inferring information about the object in hand. So our sensor is a vision-based tactile sensor. It's called Gel Slim based on the gel set technology. The sensing element is a piece of gel. It's soft and it can be deformed when in contact with another object. And the camera inside the sensor can record the images and we can recover the shape of the object, the shape of the deformation with the tactile image. Most research on the sensor before were about the reconstructing the shape of the grasp of the object, but on the mechanics side, it's an interaction with who directly causes the deformation. So instead of the shape of doing it, so my focus of the research is to reconstruct the mechanical interactions that cause the deformation, for example, the force. And I also reconstruct the slip between the object and the tactile finger. This low-level information are fundamentally important for the robotic manipulation. This figure is a exploded view of our first version of a gel slim sensor. You can see that inside here is a camera, and on the different sides we have different color of LEDs to illuminate the gels. And here is a piece of gel, and we have a transparent acrylic to support the gel. And on the outside of the gel, we print the markers and pigment to reflect the light. The gel itself is transparent. On the left side is one typical image from the camera inside the sensor, and from this color change on the gel, my colleague can use a neural network to reconstruct the contact shape. This contact shape gives us the normal deformation of the gel or the normal displacement of the gel. On the other hand, we print the markers on the gel, and we can track the markers to get the tangential information, tangential deformation of it. But what is worth noting is that because the camera is watching the gel from a tilted angle, the refraction happens and it causes the projection errors, which means even if you cause only a normal displacement, you can also observe the tangential motion of the markers in the image set because of the optical geometry. So you need to correct that projection errors to get better accuracy tangential displacement. So with the two different methods, we got both normal displacement and tangential displacement. By combining them, we got the 3D displacement field of the deformation. And the next thing we care is force. To reconstruct the force distribution, we need the material property, and we checked the material property of the gel we use. On the left hand is Young's modulus estimate. We did the tensile test of the material. We can see that it's pretty linear when the strain is under 50%. And on the right side is to check the percent ratio of the material. With that checked, we are confident that a linear FEM is proper for to map the force to map the deformation into the force field. So we use the FEM method and to generate the stiffness matrix, which is the matrix that maps the deformation field into the force field. We mesh the gel into a lot of elements, and each element is here. We use a cubic element, and by knowing the displacement of each node, we can get the full information of the deformation of the gel, and with that we can get the force distribution. And the good property of this method, because inverse FEM method, is that it can run in real time, because the time-consuming part for FEM is generating the stiffness matrix, but it can be done offline. And the tracking part, the tracking motion part, is can be done in real time. So the algorithm we have can run in real time. This is a video showing that the robot equipped with our tactile sensor is grasping a kendama, which is a ball here, and in the middle is the force distribution. It's a 3D force distribution, and on the left side is, for comparison, it's the resultant force, which we usually get with a force torque sensor. We can see that the 3D force distribution can give much richer information, and this richer information is critical for the robotic manipulation. And we also evaluated the accuracy of the force reconstruction. Since we do this by compare with a high accuracy force torque sensor with controlled experiment. We can see that in 3 directions, the force, the resultant force can match the force torque sensor very well. By collaboration with my colleague Siyu and Dong, we also use this sensor to estimate the incipient slip in the contact patch. So when the object in hand is close to slip, we can detect that incipient slip, and so that the robot can react to such slip signal. So the second part is contact perception. The question is how we can consume such tactile informations in the context of robotic manipulation. Because the information we have here with the tactile measurement is high dimensional, it's multimodality, including slip, force, and slip, force, and shape, and different channels. So how we can use such information for robotic manipulation tasks? A typical task for robotic manipulation is insertion. So with our human, we use our human hand with the capability of tactile sensing. We can easily do the insertion task. We want the robot to do the same task with our tactile sensor. And we want to discover how we can process the tactile imprints in such tasks, and how we can infer the external contact, and how we can design a control policy for this task. This video shows high resolution and high dimensional data is a burden for traditional model-based method, but it's a good thing for machine learning. So this is what my colleague Siyu and Dong did. He used machine learning, supervised learning, to label data to estimate the location of external contact. He collected data with different shapes. And this is the result. The robot, after the learning, it got a control policy, and with one poke of the object with the environment, he can estimate where that contact is and adjust the robot's motion, so that after several times of iteration, it can insert the object into the narrow space. But the problem is, what's the rational reasoning behind the working of the neural networks? It's a black box for us. Suppose a human is trying to insert an object into the hole. Key to such capability is to localize where that contact. Where is the contact between object and the environment? Even though we have no sensor embedded between the object and the edge, it's believed that the human is capable of inferring the location and direction of such a contact using tactile sensing of our fingers. So my research is trying to find the answer for this question. And we find that the key to such a capability is that with our tactile sensor, we can track the motion of the object via tactile sensor. Here is a demo video showing how it works. So the object is moving in space. We have a vacuum camera to track the motion of the object. Here is what we got from the tactile sensor. On this sensor, by tracking the markers and the geometry of the contact shape, we can infer the motion of the object. And this motion information is very critical for the previous problem we talked about. So the concept of solving this problem is because with the sensor we can track the motions of the markers in 3D space, and these markers move consistently with the rigid body motion of the object. So we can regress to get the rigid body motion of the grasped object, which includes the rotation and translation. This information, this rotation and translation is not for free randomly in space. It's caused by the external contact. It's subject to the constraints that is caused by those contacts. So if we can decode the constraint about the contact, then we can know about the contact type and the contact location. So we formulated the extrinsic contact sensing problem into a kinematic optimization problem, the kinematic constraint optimization problem. For example, on the top is the object that is in contact with the table edge, and it rotates around the table edge in different time sequence. With the tactile sensor, we can measure motions of the markers within the contact patch, and with the marker motions, we can regress to get the rigid body motion of the object, and then we solve the optimization problem to get the contact type and contact location. In the real experiment is still in progress, and we got very good at the contact estimation in simulation. The green line is the estimation, the red line is ground truth. This is also in simulation. The robot is grasping an object and moving down, and the object is moving along the table edge. Here we have designed a controller to move the object so that it can rotate the object around that corner. So for summary, today I presented our research work on the tactile sensing and perception. On the sensing side, it's about the sensor design and how we can process the low-level information to get the tactile informations. And on the second part, we talked about the contact perception, which we track the motion of the object and localize the extrinsic contact between the object and the environment. So at the end, I want to thank my colleagues for the collaboration on this project, and I'm happy to answer any questions. Thank you.
Okay, thank you very much. So it is the question time. So let me check whether there are questions coming in. I think there are a few questions like just now you have the linear relationship of your force sensor. So
Yes.
some students some audience are asking what is the range? Maybe you go back. So they want to know how big is the range.
You mean in the real experiment? What's the range of the
real
screen?
experiment? The force
mostly
sensor, I think.
It's not very much, but
oh yeah, I think it's here. Yeah.
So mostly the strain is very small because the strain is the gradient of the deformation. And the strain is the gradient of the displacement. And the displacement itself is quite small in most places. And the strain is also quite small in most different places in the contact area. The large strain area is the boundary of the contact. It's usually the boundary area. That's where the accuracy is lower because at that contact edge, contact boundaries, the strain may be larger than 50%. But in most places, the strain is well below 50%. So the linearity is very respected.
Okay, so another question which has common interest is your material. So I think it's, you mentioned it is gel. So can you elaborate it? And how do you make it like it is liquid or solid, and how to make it into solid?
It's just we bought the recipe from the commercial vendors. I forgot the name of that gel. It's a specific gel because we need the gel to be transparent. So we have not much options, and we need also that the material is as linear as possible, and we don't want heuristic of the material. So how do we make it is we bought the raw material, which has part A and part B, and we also have a part C to adjust the thickness, the Young's modulus of the material. So with different ratios of A and B, you just put them together and mold them into the shapes you want. Typically, we use a flat surface. So we make a large piece of a flat gel, and we cut into, after we make it, it cure in like 24 hours, or if you place it in the oven, it can cure like within an hour. And with the cured gel, you can print the imprint you want, and you print the markers onto it. And with that, you cut the gel into the shape you want, and glue that onto the sensor.
Okay. So how about the lifetime?
The lifetime, this gel is quite strong. So we did the enduring test, and with one piece of gel, we did experiment for over 20,000 grasps. We use the sensor, we use the robotic hand, the finger, to grasp object, and with over 20,000 grasps, it's still like new. So it's quite strong.
Okay.
We can use it for months.
Yeah. So for interested audience, maybe you can separately contacted Dr. Ma for the recipe. He said he forgot the recipe, but it is available from market. So if you are interested in it, you can contact him. Is it okay, Dr. Ma?
Thank you, Professor Chen.
Okay, so another question from YouTube is that you did a simulation for your second half. So which simulation platform do you use for the 2-finger grasping?
I programmed it myself in Python.
Okay. So then you can patent it, then people can use it. Okay, so any other questions from the audience? Let me check. Yeah, so if we don't have, actually I have a question from myself because I don't know such things, so I'm quite curious. So when you talk about the force, when you want to grasp different objects, you should have a consideration of the force. You cannot make the force too large or too small. If it is too small, you cannot grasp it. If it is too large, then you may perhaps destroy the object. So you need also to have the accuracy, a certain accuracy of the force you estimated. So what is your consideration when you do such things, do force estimation or sensitive? Yeah.
So let's say we haven't calibrated those like the full range of that measurement, but we can definitely measure the force between like 0.2 Newton to like 20 Newton or 50 Newton. So it's reasonably large for the robotic manipulation. But if you want to measure very small, very sensitive contact forces with our current sensor, no, but you can always tune the stiffness of the gel to your task, to fit your task. You can, because that gel, you can make it yourself, and by changing the ratio between part A, part B, and part C, you can make it soft, make it hard. When you make it softer, you measure smaller force, and you make it harder, you can measure a larger force.
Okay, thank you very much.
Yeah,
I think you have.
I have a question. Yeah, so Dr. Ma, you have the work is very interesting. I was very kind of fascinated by the work you did. I'm wondering, what is the highest depth resolution you can sense?
Right now, usually like 0.02 millimeter.
Okay, it's 20 microns.
It's something we can measure.
Okay. So what about spatial? Is it spatially how small like features you can sense?
Spatially, you mean?
Yeah, X and Y.
The scale of the object?
X and Y. So
spatial resolution.
Spatial resolution is right now. So the force spatial resolution is one measurement every 1 millimeter.
Okay.
Yeah, but the geometry can be much higher because the geometry measurement is based on the color, which is you can get from the pixel size, not by the distance between the markers. So with that, you can get like, let's say 0.08 millimeter per pixel.
0.08,
so
okay.
That's the distance. Yeah.
So it's about 80 microns.
80
okay.
microns.
Great. Yeah, this is I keep a close look at this work because it was very interesting even for 3D like sensing.
Thank you.
Yeah, because there are some challenges. This is a technology for something very shiny, so this technology can work very well.
Thank you.
But optical technology has a problem doing this.
Okay,
yeah, that's my question.
Thank Prof. Thank Prof. Zhang for your question, and thank Dr. Ma for your answering. So because of the time, we stop here, and we needed to move on to the next speaker. So my job is done. And again, thank you very much for two excellent speakers, Dr. Zhao and Dr. Ma. I'm really honored. So now Professor Liu will take me over to chair the rest of the session. So Prof. Liu, it's your turn.
Hello, everyone. It's a break time. Hello.
Hi, can you hear me?
Yeah. Okay. Hello, everyone. Let's continue our meeting. I'm Xiaoli Liu from Shenzhen University. It's a great honor to chair this session with Professor Qian. Next, I will be honored to introduce the next speaker, Dr. Jason Yang. Dr. Jason Yang is currently a senior system engineer at Orbex 3D. He is mainly focusing on the 3D optical sensing system development based on structured light, embedded system design, and embedded system programming. He received the master degree and PhD degree in the School of Mechanical Engineering from Purdue University and the Bachelor of Science degree from Yonsei University. Now let's welcome Dr. Jason Yang.
Thank you. Good morning, everyone. It's a great honor to do my presentation in front of you. This is Jason Yang, and a senior system engineer at Orbex 3D. So my research topic is about high accuracy, high speed 3D optical sensing. This is the outline of my presentation. First, I will start with the introduction and background of my research. After that, I will explain two main research topics that I have done and briefly explain the project that I'm working on to commercialize the 3D scanning system. A lot of topics are related to my graduate studies, and I will briefly introduce the project that I'm working on. Okay, over the past few decades, automation in manufacturing has led to highly increased productivity and efficiency. In addition, there has been a lot of effort to minimize the defect rate of final products. For this reason, numerous sensing technologies are developed and used for inspecting products and supervising processes in detail. Especially accurate 3D sensing is of great importance to manufacturing process for quality control. Even if there are accurate measuring tools using contact method, it is more desirable to use non-contact method because of much less time required to inspect one product. Here are two representative examples of using 3D scanners to inspect products in manufacturing line. The 3D scanner in structured environment, which is well-controlled area, works well. However, it is difficult to apply the same 3D sensing technologies in unstructured environment. From construction site to our daily life, there are numerous variables making our environment unstructured. For example, changing lighting conditions in construction sites make it difficult to scan the surrounding environment, and turbid air blocks the scanning area, which may result in a poor 3D result. For autonomous vehicle detecting moving objects near the vehicle in real time or running the vehicle on the road with no traffic lights or worn-out lanes are still challenging problems. My research focuses on developing algorithm and scanning system by giving accurate 3D information fast for this unstructured environment. Before explaining the technology I use, I will explain the fundamentals of standard stereo vision system. The fundamentals of stereo vision system is similar to how we recognize the word in 3D. We captured an object with two cameras at different angles. The processor finds out the corresponding points between two images, and by using the triangular relationship, we can reconstruct a 3D. For sure, there are pros and cons. The advantage of using the standard stereo vision method is that it is easy to implement. Only two cameras are required to set up the system. Second, it is suitable for high-speed applications. Since only a single shot from each camera is required to reconstruct one 3D image, which means that the camera capturing speed is equal to 3D image capturing speed. However, the computer is not as efficient as our brain. The computational cost of finding the correspondence is really high. If the object does not have texture variation on the surface, or the texture variation is repeated a lot, it is difficult to obtain accurate correspondence between two images as shown here. Therefore, we use digital fringe projection technology to reconstruct 3D. The only different thing is that one camera is replaced with one projector. The projector projects the pattern, which has many stripes. We use a trigonometric function to generate these gradually changing patterns, which is called as fringe pattern. We project these fringe patterns onto the object, then the pattern will be distorted, depending on the geometry of the object. For example, if we project these patterns on the wall, we can see the stripes with less distortion. However, if we projected the pattern on the object as shown in this figure, the pattern will be distorted a lot. The camera captures the object image with the pattern, and the 3D information can be obtained by calculating the level of distortion inversely. In digital fringe projection technology, phase shifting algorithm is extensively used for 3D reconstruction because of its robustness, high spatial resolution, and high accuracy. Since I shifted the stripes in a certain amount of pixel for each pattern, I refer to it as phase shifting algorithm. I can describe the patterns mathematically as shown here. The right image is a photograph of the object. This is I1, and this is I2 and I3. As you can see in this figure, the stripes in the pattern are shifted. I prime is the average intensity and I double prime is intensity modulation, and phi is the phase value to be solved for. I have three unknown I prime, I double prime, and phi, so to solve for the phase, the minimum number of patterns is 3. With these 3 patterns, I can calculate the phase by using arctangent function. Because of the use of the arctangent function, the phase ranges from -pi to pi, and repeats the range for every period, which is called as rapid phase. To make the phase continuous, I need to unwrap the rapid phase. If I can make an order for every period and add or subtract the multiples of 2 pi to the rapid phase, I can make continuous and uniquely defined phase value, which is called absolute phase. After I get unwrapped phase, I can reconstruct 3D by using the triangulation relationship of the system. As I mentioned before, the system consists of one camera and one projector, which follow pinhole model. This system is denoted by 2 equations under the first bullet, which represent the transformation from world coordinate to imaging plane. In these 2 sets of equations, the extrinsic matrices describe the relationship between world and lens coordinate. The intrinsic matrices model the projection from 3D lens coordinate to 2D imaging plane. Intrinsic and extrinsic parameters can be obtained by the system calibration. So the camera calibration is a well-known studied problem in the computer vision field. One widely used method is to put a calibration board in front of the camera and adjust it to different poses. By detecting the featured positions in the camera image, such as the positions of surgical centers in this example, it can use an optimization algorithm to solve for the parameters of the camera. Different from a camera, projector cannot directly see the calibration board. To address this problem, I can take assistance from a camera and build a relationship between camera and projector images. Like this example here, I can use projector to project some fringe patterns onto the calibration board and use the camera to capture those patterns. From camera captured images, I can obtain phase map. Through this phase map, for specific point on the camera image, I can determine its corresponding projector pixel to be on a unique vertical line of the pixels on the projector imaging plane. Similarly, if I use some horizontal patterns, I can determine that the corresponding projector pixel is on a horizontal line of the pixels on the projector image. Then the intersection of the vertical line and the horizontal line is the corresponding projector pixels of the camera pixel. Based on this strategy, I can build a precise mapping relationship between camera and projector images. Therefore, I can let the projector see a calibration board and use a previous camera calibration method to calibrate the projector. After calibrating two optical devices, I can get two sets of equations for each optical devices. Since there are three equations for each optical device, the number of equations I have is 6. However, the number of unknown is 7. Therefore, I need an additional equation. The unwrapped phase provides one more constraint to calculate the 3D information. This is how the digital fringe projection system reconstructs the 3D. For the digital fringe projection system, it is really critical to achieve highly accurate unwrapped phase value. I will explain the representative way of unwrapping the wrapped phase, which is gray coding. By adding more binary patterns, we can determine the fringe order for each period, and based on the fringe order, we can accurately calculate the unwrapped phase value as shown here. The gray coding method is an intuitive way to understand and works well in measuring static objects. However, it's not suitable for high-speed experiment, since the number of additional patterns depends on the number of period in the fringe pattern. If the number of period is large, the number of additional binary patterns required to calculate the fringe order should become large. So for high-speed experiment, we typically use different phase unwrapping method instead of gray coding phase unwrapping method. One of them is two-frequency phase unwrapping, which requires only 6 patterns, 3 for each frequency. First, I need a set of patterns with different frequency. So here on the top left, there is high frequency pattern, and underneath it, there is a low frequency pattern. As you can see here, the low frequency has only one period, which covers the whole pattern. If we apply the arctangent function, respectively, to these patterns, the phase of the different frequency is obtained as in the middle figures. We call this phi, h, and pl. Since the low frequency phase has only one period in the pattern, there is no need to do phase unwrapping process. Now moving on to the third row of the figure, in order to calculate the fringe order, the first step is to multiply the scaling factor TL over TH to low frequency phase PL. TL over TH is the fringe width of low frequency over the fringe width of high frequency. Then I subtract the high frequency wrapped phase VH from the multiplied phase value, and then divide all of this into 2 pi, which gives the fringe order K. We then multiply this fringe order K with 2 pi and add them to high frequency wrapped phase VH, and ultimately we obtain the unwrapped phase value. Although this algorithm works well in ideal case, there is a limitation when applying this to the real data, which is noise impact. So as in the previous slide, we multiply the scaling factor TL over TH with low frequency phase VL to calculate the fringe order K. The problem is that the noise inside the low frequency phase is multiplied together. Let's look at this example. The scaling factor is 38, so 1140 divided by 30, which is same as in the previous slide. But when we multiply this scaling factor with the low frequency phase, which has noise, we get a result where noise is multiplied by 38 times. So we get this wiggly line as a result. This necessarily results in the incorrect fringe order K, which causes wrong unwrapped phase and also wrong 3D sensing result, as you can see in the last figure. So I developed a new method to unwrap the low frequency phase by using geometric constraints. To minimize the noise impact, there are two ways to reduce the scaling factor. The first one is to make the TH larger, or second one is TL smaller. If I make TH larger, I can reduce the number of periods. However, I may lose the details of the data. On the other hand, if I make TL smaller, the low frequency pattern would have more than one period. So it can no longer cover the whole pattern. This means that I need to apply another phase unwrapping algorithm to unwrap the low frequency wrapped phase. Suppose we succeed in unwrapping the low frequency wrapped phase. In other words, let's say we obtain VL somehow, then the scaling factor would become smaller as TL gets smaller. So we can reduce the noise impact. Then my question is how to unwrap this low frequency wrapped phase and obtain VL. The solution that I came up with was using artificially generated phase map, which is VA, the red line in this figure. Let me give you an example. For the first period, the phase value is larger than the artificially generated phase, the red line. So I do not have to do anything. But for the second period, it is lower than the artificial phase value. So I added 2 pi on the second period. For the third period, the difference is larger than 2 pi, so I added 4 pi for the third period. By using this method, I could successfully unwrap the low-frequency wrapped phase, and the final result we get is the noise-reduced unwrapped phase. So in the previous slide, we learned that in order to calculate the low-frequency phase, we have to generate artificial phase map, the VA, the red line in the previous figure. Here's the brief description of how I calculate the artificial phase map. I mentioned previously that we got 6 equations and 7 unknowns through the camera and projector calibration. In order to reduce one unknown variable, I set a virtual plane, which is an imaginary wall at a distance of z mean. So now I can solve the equations as I have 6 equations and 6 unknowns. In other words, I can uniquely obtain the projector pixel UP and VP for each camera pixel UC and VC. Now that we figured out values for the variables that are required to calculate the artificial phase map, we can obtain the artificial phase VA. This is an experimental setup to validate the performance of the algorithm. I use CMOS camera and digital light processing projector for the experiment and set the fringe width of high frequency phase at 30 pixels. For the fringe width of low frequency phase, I set 1140 pixels, which covers the whole pattern within one period for existing method, and 228 pixels, which is 1/5 of 1140 pixels for developed new algorithm. In this case, I can reduce the noise to 20% by using the developed algorithm. These are experimental results. To see the difference clearly, I compare the unwrapped phase map and 3D results respectively. If you look at these close-up views, you can easily find the difference between two results. The unwrapped phase with existing method has phase unwrapping error on these parts. And result in the wrong 3D. From now on, I'm going to introduce the second project. The second research topic that I've done is about the systematic development in DFP system, which is mechanical projector. Typically in digital fringe projection system, digital light processing projector is used for 3D reconstruction. Inside the projector, there is a set of micrometer called digital micrometer device, DMD. This micrometer are made of silicon, which can reflect a certain range of lights, which means that using this DLP projector is difficult to use near infrared and infrared light to project invisible patterns. So to overcome this light spectrum, I developed a new hardware setup called mechanical projector. To generate the pattern, I use a metallic wheel which has many spokes. Since it is made of steel instead of silicon, I can use broad light spectrum. By adjusting the distance between the lens and the object, I can defocus the pattern. Then I can generate the same fringe pattern which DLP projector can generate. So to apply the phase shifting algorithm, we need to synchronize the high-speed camera with the mechanical projector precisely. We use a high-performance microprocessor to achieve high speed and high accurate synchronization. This is an example of the synchronization. We use 3-step phase shift pattern, which means that each period has 3 patterns. We use a photo interrupter to detect the signal of the wheel, and the processor divides the period into 3 intervals and sends trigger signal to the camera for capturing images. To reconstruct 3D, I need to unwrap the wrapped phase, which requires additional set of patterns in different frequency. However, if I add more patterns, the measurement speed slows down since the number of patterns for one 3D image become large. So instead of using additional patterns, I printed out this statistical pattern on the transparent film and inserted it in between the wheel and object. As a result, I get this encoded fringe pattern. This is the computational framework of how I can reconstruct accurate 3D in high speed. By rotating the wheel, I can get a ton of encoded pattern images as shown here. Then I can calculate the average intensity which has statistical pattern on the object. With a standard stereo vision algorithm, I can roughly reconstruct 3D, which is ugly cat here. Oh, it is ugly cat here. Meanwhile, I can calculate the phase value using phase shifting algorithm, and this phase value refines the rough 3D, which results in the big cat on the right side. Let me explain the refinement algorithm in detail. This is the image captured by left camera, and this is the image captured by the left image, and this image is captured by the right camera. To help you understand the algorithm, I set 1 pixel on the left image and marked the pixel in yellow color. With the standard stereo vision algorithm, we can roughly find out the corresponding pair of the pixel on the left image with the texture value, and the red dot means the matching point on the right camera image. Then we turn into phase domain. White dot means surrounding pixel of the red dot. By comparing phase value of the surrounding pixels one by one, we try to find a value of tau 0 and the pixel which satisfies this inequality. I reduce the inequality. The pixel is marked in orange color. After that, to achieve sub-pixel level accuracy, we interpolate the phase value linearly and obtain the value of delta tau. Finally, we can achieve very accurate corresponding pair for 3D reconstruction. This is the experimental setup of the mechanical projector. I use a halogen lamp as a light source and an optical fiber to deliver the light independently. To generate the encoded fringe pattern, an optical chopper is used for generating fringe patterns, and a statistical pattern printed film was attached in front of the wheel. The leftmost image is a photograph of the object, and the next one is a representative fringe image that I captured. By averaging the fringe images, I can get texture images with statistical pattern. The two images on the right are the 3D results I got using the system. By comparing the two 3D results, you can see that the mechanical projector and the refinement algorithm significantly improved the 3D reconstruction. The contribution of this research is very clear. The first one is to achieve a speed up to 10,000 3D images per second. And we can get, second one is we can get the sub-camera pixel accuracy. Third one is I can also utilize broad light spectrum, such as visible, IR, and UV light. So from now on, based on the research that I have done at Purdue University, I got an opportunity to commercialize the 3D scanning system with the structured light pattern that I've studied. It is a great chance for me to connect my PhD research into the industry in order to commercialize the product. I know that it is a rare case to have the experience of developing the system that I worked during my graduate study. I briefly introduced the project, but a lot of things are confidential, so I'm gonna briefly introduce the project. So this one is a portable all-in-one inspection system by using the algorithm that I've developed. The company is trying to develop the portable 3D scanning system. This system is fully portable with battery and has the embedded processor inside it. So the only thing that the user had to do is just connect the USB storage to save the 3D rendered file. In addition, the system has the dual resolution cameras to capture both large field of view and small field of view for detail. So this is the only images that I can show you. So these are the preliminary results that I got using the portable 3D scanning system. The most left image is the object to be captured. In this case, I captured two shoes. The sole of trekking shoes has a lot of bumps to maximize the friction force, and these bumps are good objects to show how much detail the system can reconstruct. The figure in this middle shows the 3D results captured by a large field of view camera. The 3D geometry of the shoes are calculated by using the fast and efficient reconstruction algorithm that I briefly explained in the previous slide. The most right image is the 3D result captured by a small field of view, which has high resolution for highly detailed inspection. As you can see in this image, even very small bumps can be captured and reconstructed in 3D. And for sure, we can save the RGB texture file in this 3D rendered file. So this is at the end of my presentation. Thank you for listening.
Okay, thank you. There are some questions. The first question is, does the line scan camera have application prospects in 3D imaging? Light camera.
Could you
Light
repeat
scan camera.
Could you repeat the question again? I couldn't get it.
Does the light scan camera has application prospects in 3D imaging?
Light scan camera?
Yeah. Light scan camera can be used to 3D imaging.
The system that I developed can be used for 3D imaging? Oh, sorry, my bad. So your question is that the algorithm and the system that I've developed can be used for 3D imaging or light scanning?
I think usually we use a two-dimensional camera, just a plain array, two-dimensional array. But we do have some cameras actually line array, one-dimensional. So the question is, how do you think about this question, whether this kind of 1D array camera is useful?
I think 1D camera can use for 3D reconstruction, but the reason for using 2D cameras is that we can get high spatial resolution. I mean, by capturing just several shot of 2D images, we can reconstruct full 3D model of the object. That's why we try to apply just 2D cameras to our system. But for sure, I think we can use the line camera to reconstruct 3D.
Maybe I make, sorry, can I make a small comment?
Okay.
Yeah, so because we happen to write a review paper on line array camera. Actually, the paper was written mainly by Dr. Wang Guohui from Xi'an Gongye Daxue. So he has done a lot of work on the application of this kind of line array camera. This kind of line array camera not very popularly seen in our clinics, but actually it is very, very useful for high speed requirement. If you have high speed requirement in your project, then a line scanning camera will be very, very useful. So the audience, if you have interest, you can contact Wang Guohui 教授 西安工业大学. He has done a lot of work. I think he's also writing a new review paper on line scan camera applications. The previous paper is on calibration. 他前面写了一篇综述文章，是各种各样的 calibration 的方法，他做了一个 review。那他现在在写第二个 review 是各种各样的 application. So audience, if you have interest, you can
Okay.
contact him.
Okay. I'm really interested in the topic. So line camera is okay. I got it. I'll ask you later about the details.
So you can understand Chinese.
I'll ask you later about the details. I think it'll be a great chance to learn from others, I think.
Okay, the next question is how about the time cost for refinement algorithm?
Time cost?
Refinement algorithm.
Refinement algorithm is basically, you mean the mechanical projector? You mean this one? So your question is about the time cost, right? Computational cost for this refinement algorithm?
Yes. So go ahead and answer the question.
Basically, we developed this system. We capture, because we use the system very high speed camera. So after capturing tons of images, and after that we process this refinement algorithm and reconstruct 3D. So we actually, for this project, we does not care about the speed of the refinement algorithm, but the only thing we have to do is just apply the standard stereo vision algorithm, and after that we compare the phase value. So depending on how fast the standard stereo vision method, we can refine the 3D research very well, because by comparing the corresponding pairs based on the phase value is really easy, and based on the linear interpolation, so the computational cost for the detailed refinement algorithm is much lower than the standard stereo vision. So the bottleneck is the standard stereo vision method. That's the thing that I can tell you. But actually, for this project, we does not care about the computational costs for the refinement algorithm.
Okay, thank you.
Thank you.
Thanks for Dr. Johnson Yuan's wonderful report. Thank you.
Thank you.
Okay, the next special lecture is being presented by Dr. Charles Ri Zhongtai Qi. Charles He is currently a senior research scientist at Walmart Limited Liability Company. Before that, he was a postdoctoral researcher at Facebook AI Research. He got his PhD from Stanford University in 2018 and his Bachelor of Engineering degree from Tsinghua University in 2013. His research focuses on deep learning, computer vision, and 3D with well-known publications in CVPR, ICCV, SIGGRAPH for Asia. Some of the 3D deep learning and 3D object detection models have been widely adopted in both academic and industry. Now let's welcome Dr. Charlie Qi to report.
Yeah, thanks for the introduction. Hi everyone, good morning, good afternoon, good evening, depending on where you are. So I'm happy to be here today to share my works on 3D object recognition in point clouds. And really thanks for the organizers and volunteers for this online forum. I think it's a great opportunity for everyone to share and learn. I also learned a lot through the talks. So in this talk, in the first half, I will introduce the recent progress on developing deep neural networks to process 3D point cloud data. And then in the second half, I will introduce two methods to utilize those representation learning networks for 3D scene understanding, specifically solving the 3D object detection problem. So as a motivation, why we care so much about learning point cloud features. So recently we see emerging applications that involves 3D perception of the environment. For example, in autonomous driving, the robot car needs to perceive where pedestrians are or where other cars are in order to plan its action, also understanding the environment motions. And with this, we really need 3D data and 3D scene understanding. Also for augmented realities, now most devices like AR glasses or even your iPhone, iPad, they are equipped with 3D sensors like depth camera or even LiDARs. Then we need to use those sensors to understand the indoor environment. So in order to place virtual objects to create a mixture experience. For all those emerging applications, we need to understand the 3D scenes. However, it's really hard to write a program to solve this. We need a data-driven method. And that leads to a very strong need for 3D deep learning. However, different from image representation or audio representation that has very classical data format, like 2D pixel arrays for images or 1D array for audios, 3D has many different classic representations. Here lists a few of them. For example, in point cloud, we have a set of points in, say, XYZ coordinates. And for meshes, it's popularly used in graphics. We have a soup of polygons or chords. And in volumetric representation, we quantize the space into small cubes or voxels. And also we can represent 3D through projected views as a multi-view images either in RGB or RGBD. Among those representations, I want to argue for perception problems, point cloud is very special for two reasons. One is that it's probably the closest representation to raw sensor data. When we use LiDAR, when we use depth sensor or scanning, we got point clouds. And secondly, it's very representationally simple, meaning it's just a set of points. It can be easily converted from other representations or to other ones. In comparison, the rest representations, they are more complicated. Like for meshes, you need to determine the connectivity using triangles or chords. For manometric, you have to determine the resolution. For multi-view, you have to determine the view angles. So you have more hyperparameters in the choices. besides depth sensors, we also can get point cloud from structural motion or stereo vision. So there are really many sources for 3D data nowadays. And that's why it's so exciting to work on 3D deep learning, because there's a closed loop of getting data, understanding data, and getting more data. However, historically, point cloud features are mostly handcrafted. So they are designed for different specific tasks and can be very hard to optimize if you want to have a really challenging perception problem. So the research question we asked then was that, can we learn effective 3D features directly on point clouds without any pre-processing or pre-feature extraction? To answer that question, we proposed a PointNet in 2017 in the CVPR paper we have then, where PointNet is an end-to-end learning neural network for irregular point data. And it provides a unified framework for various tasks, ranging from classification to segmentation or to semantic scene parsing. For example, given a point cloud of an object, the network can be used to classify the semantic class of that object, whether it is a table, a car, or a mark. It can also be used to segment the point clouds into different semantic regions, like different parts of an object or different regions of an office room on the right, like whether it's a chair, whether it's the wall or the floor of the 3D environment. The design of the model, actually, it was motivated by the two properties of point clouds. The first one, we will be focusing on the first one for this talk. The first one is permutation invariance. A point cloud is very special because it's a set. So for a set, it doesn't have any orders. So any network that operates on this set should be permutation invariant. Let me dive a little bit deeper into it. So usually we represent a point cloud as a 2D array. Here we have n unordered points. Each point can be represented by a d-dimensional vector. Then we have an n by d array. This array, however, is very special because if you switch the rows of this array, it still represents the same set, although it's a completely different array. So whatever network or machine learning model that operates on this array needs to be n factorial permutation invariant. So how to design this? As we understand, whatever machine learning model is still a mathematical function. So what is the mathematical function that's permutation invariant? We call it a symmetric function, meaning that if you switch the orders of the input elements, the function will give you exactly the same output. We are actually familiar with many such functions. For example, if you do a simple max operation, it is symmetric. If you do a summation, it's also symmetric. So then the question is, can we design or construct a family of symmetric functions by neural networks? So we approach this from the simplest form. Okay, we don't have any learnable parameters. We just do a symmetric operator. Say this time it's a max. We take the max along each channel of the point. So here we list a list of points. First point is 1, 2, 3. So then after this max, we get this extreme point. However, this naive design just discovers very extreme or naive property of the geometry. We lose the interesting information because the max is too rudimentary. So rather than directly using the aggregator, we can first embed the low dimensional channels of the coordinates into a much higher dimensional space before the aggregation. For example, we can embed the 3-dimensional XYZ to 1,000 dimension. Then we use the aggregator to compress them into a single feature. And then we can follow on with some other processing network, gamma, to further process the point cloud features. So in composition, this is a composition of gamma, G, and H. And since the H function is shared across all points, then as long as we guarantee the function G is symmetric, then the whole composition of function is guaranteed to be symmetric. We call this form a PointNet vanilla. Empirically, we use multi-layer perceptual networks, which basically are fully connected layers with nonlinear layers and normalization as function h, and use max pooling as function g. You can also use other average pooling, weighted average pooling as well. And we can use another multilayer perception network for the function gamma. Interesting question, something you may wonder is, what does this function h learns? It sounds like a miracle, magical function, just projects 3 channels to 1,000 dimension and just works. So we can do that by some visualization. So it's actually function h acts as a soft voxelization. So it's dividing the space. For example, if we have 1,000 dimension output from function h, then each dimension actually corresponding to a region of points. So the visualization shows which region of the points will activate each channel of this 1,000 dimension. We see some of the channel, they are in charge of the top, bottom, or some of them in charge of the ceiling, in the floor of the point cloud space. And this soft voxelization is learned in a data-driven way. So depending on data, the network will be able to optimize for that. This is in contrast to a fixed voxelization where you divide the space by some fixed rule. And here we show some visualization results of the network operating on semantic segmentation task. So with the learn feature, we can use supervised learning to supervise the network to segment objects into different semantic parts. It works well both on partial point cloud input on the left and complete point cloud on the right. And here we show more semantic scene parsing results. First row shows a rendered view of a 3D point cloud scan from indoor rooms at Stanford, actually. And second row shows the semantic parsing results where we see the network can distinguish floors, tables, chairs, monitors, etc. pretty well. And furthermore, besides the good performance, the point net is also very robust to data corruption. Here we show when we miss data, like throw away points, how the classification accuracy drops in different networks. So the x-axis showing how much data we throw away from 0% to 20%, like 100%. And the y-axis shows the accuracy. And when compare point net with the voxelnet, which is the VoxNet, which is the 3D convolutional neural network, we see that even when we drop more than 50% of the points, the accuracy just decreases by a very little 2%. So that means that the network is very robust to missing data. Why is it so robust? We are trying to understand that through a visualization. So we here want to visualize what points contribute to the global feature. Remember, we have this max pooling. So some point will have very small features. So after max pooling, that point may not matter for the global feature. So the first row shows original shape point cloud. Color shows the depths of the points. And second row, we show which are the points that contribute to the global feature. We see that the point net is able to capture those skeleton or contour points that are perceptually very interesting points. So as long as those points are mostly kept, then missing other points won't affect its classification ability. So that's a very nice feature for sparse point cloud. And moving on, like after this work, we further extend the network to a kind of V2 version called PointNet++. Remember the design of PointNet, they take coordinates and project them into high space. Now, if you have a very large scene, the coordinates can vary a lot, like from negative 100 meters, positive 100 meters, right? So the idea of PointNet++ is instead of applying PointNet globally, it applies PointNet at local regions. So at every local region, we apply a mini PointNet and aggregate features. Now where this local region will become a new point with features. In this way, we can achieve hierarchical feature learning, and also the network can be translation invariant because everything is local. And then still, because it uses PointNet, it's still permutation invariant, which is nice. And if we repeat such structure of local PointNet pooling, we can achieve multiple layers of this so-called set abstraction to achieve hierarchical feature learning. And after this, we can max pool all the features for classification or have some up convolution for per point classification, which is segmentation. And by using this PointNet++, we show that it gets better semantic parsing accuracy because it has this hierarchical learning compared to PointNet. Okay, so that's the first half. I've talked about the deep neural network we designed for 3D representation learning. And next, we want to see how we can use this for 3D scene understanding. So specifically, we care about the key problem of 3D object detection. So this is based on our ICCV 2019 paper called Deep Half Voting for 3D object detection in point clouds. So first, for people who are not familiar with the problem, 3D object detection is trying to localize objects in a 3D scene and also estimate their semantic classes. So we will output oriented 3D bounding boxes for objects and as well as their classes. It's a very key problem in many applications, for example, in autonomous driving. However, prior work mostly relies on 2D object detection, even though it is a 3D problem. On the left, we show a typical way of detecting objects in outdoor LiDAR scans. People first convert the point clouds into a bird's eye view, meaning you look the point cloud from top to bottom, and then it has 2D detectors on this bird's eye view images, so there's no 3D operation anymore. On the right, we show that it's a cascaded system called Frustum PointNet, where it first localizes the object in 2D image, and then the 2D image will specify the 3D Frustum space where the object could be in. Then it localized the object in that Frustum, but it's depending on the first step where you localize objects in a 2D image. Another way, there are methods that you don't use 2D networks, but architecture is like 2D ones. So this 3D convolutional neural network detector, they leverage 2D detector structures like a region proposal network, faster RCN network. However, because it's operating in the voxel space, it's really computational heavy because there are many empty voxels in this 3D space. But for the detector, you still need to scan through those empty spaces, which is really, really costly. So the research question then was that, how can we design a 3D object detection framework from first principle, not relying on 2D detectors? So if we observe the differences from 2D image and 3D left and right, we see that 2D images have very dense pixels. It really makes sense to do a dense sliding shape. Like basically that's what convolutional neural network is doing to propose regions and recognize objects. However, in 3D, we have very sparse point cloud. Many spaces, they are empty. We only capture the surfaces of the objects. So instead of sliding through all the possible 3D spaces in the space, which mostly is empty, our approach is voting. So instead of sliding through everywhere, we start from the surface points, and they try to vote for where the object centers are. And then through those votes, we can learn to regress the 3D bounding boxes for the scene. Actually, this idea is not new. Like 40 years ago, people have proposed this idea called generalized half voting, half transform. Basically, it's like voting from local patches. However, in these older works, everything is based on handcrafted features and the module is not end-to-end optimizable. It's really hard to tune. In our design, which we call VoteNet, we have entirely differentiable end-to-end network, emulating the structure of this generalized half voting. So here it is. It's called a VoteNet, also called deep half voting. So first we have a point cloud. We will first use a PointNet++ to learn the local features. So we have some seed points with XYZ and also learned features on them. Then we supervise the features to vote for the object centers. Then we will see a natural clustering of the votes around the centers of the chairs and tables in this example. And then each vote having both XYZ and features, they can be in parallel processed to be aggregated to propose bounding boxes. So compared to the traditional half voting, we don't do any explicit clustering, but we can process this in parallel in a learnable way with GPU. Then we will get bounding boxes through supervised learning. And after maximum suppression, we have pretty good 3D detection results. And the entire network called VoltNet is end-to-end differentiable and optimizable. It got state-of-the-art results when it was published on several data sets. So here we show some results on one of the popular data sets on RGB. On the last column is the ground truth. The first column is the image. However, the image is not used here. In the middle column, we show the VoltNet prediction, which is really accurate. And also, interestingly, it captures some chairs even not annotated in the ground truth. And we also show the results on ScanNet, which is compared to some RGBD, which is a single view depth scan. This is a fused reconstruction of indoor environments. Also did pretty well, even in very crowded things. After this, remember that we just use point clouds for the VoltNet deep half voting. We wondered, can images help the VoltNet detection? Because in images, it has some complementary information. Like it is high resolution, it has RGB color, rich texture. And also some cases, the scanner may not scan well on some surfaces, but you can see clearly the objects in images. So we have this other work called Image VoltNet, published in CVTPR 2020, which leverage image semantic features like semantic class, 2D boxes, but also image geometric features. The 2D votes from a pixel to the 2D box center, we can lift it up through the camera parameters into 3D and fuse all those semantic geometric information in both 2D and 3D for the detection. I won't go deeper into the details, but I want to show some interesting example results. So here we compare the image VoltNet results and the VoltNet one. The image VoltNet also uses the image. So see this black sofa, because the material is not very friendly with the depth camera, we don't get many points from the sofa. However, with the image, we can still recognize it well. And in the second row, we can recognize further away objects with less points because we can detect them in the image. Okay, so here's a brief summary. So 3D deep learning is really a rising field. I talked about two aspects in this talk. One is how to do 3D representation learning with PointNet, and then how to utilize those networks to design a framework for 3D object detection. And I also want to use 2 minutes to introduce a few research opportunities we have met at Waymo. So at Waymo, it's really 3D core problem. We have 3D data input. The car needs to make 3D decisions, 3D predictions. It's really beyond perception. Then it's really interesting to think how we combine this train of perception, behavior prediction of this, for example, this bicycle carting in front of the car with the planning. It's a really more complicated system with much larger design space. And also at Waymo, we have very strong LiDAR sensors. It gets very high resolution point cloud, close to image resolutions. How to make the best use of this sensor and design novel 3D learning networks is also an open question. Also, we face scalability problem. We want to have the algorithm work in more than one types of cars, more than one types of cities, more than one types of weather, how to tackle the domain gaps between those different use scenarios. It's a challenge for machine learning models in general. And also we are actively working, collaborating with academia through publishing this open data set where we release more than 1,000 round segments of 20-second videos with all the sensor data, a lot of annotations to support collaborative progress from both industry and academia. So that's my talk. Really thank you for listening. I'm welcoming any questions you may have. Thanks.
Okay. Thanks, Dr. Charles. Interesting report about 3D point cloud classification, segmentation, and detection. Is there any question?
So Dr. Qi, I have a couple questions. So one question I have is that for the point cloud data you have, right? Do you do any pre-processing before you kind of do segmentation?
Yes. So the pre-processing is really lightweight. So it's mostly normalizing and scaling the point cloud to the right scale and coordinate system.
Okay, so you didn't do like denoising, in other words.
Usually okay, so it depends, right? So most applications we may not need a denoising, but there can be long tail or edge cases. For example, if you have a mirror or you have a sprinkling water or fog, then you may have noisy point cloud. Or if you have a reflective objects, then you may need to denoise those points. But then those are mostly, limited by the sensor you have. If you have a perfect sensor, then you probably won't need a denoising. Otherwise, there are those long tail cases where it's needed.
Okay. Yeah. So that is my first question. So second question is that so look like your segmentation, like machine learning based, all this segmentation work you did, right? So primarily like indoor applications. Have you tested like outdoor applications, like sensor data from, you shoot from LiDAR and also, 2F sensor, right? So I'm wondering whether this kind of algorithm can work well for that situation.
Yeah, definitely. There are also a lot of work that use the similar architecture on outdoor scans, whether it's from LiDAR or from, fused LiDAR reconstruction. There are a lot of them, and they do work really well after careful tuning.
I see. I actually tested, last year was in San Francisco. I sit in one of the Waymo car. That was very cool.
Oh, wow. Yeah, that should be a good experience.
Yeah, it was a very good experience. Yeah. Thank you so much. That's very nice talk, and also great work.
Yeah, thanks.
Okay. Other question? Okay, no question. Okay, thanks, Dr. Charles. Wonderful report.
Thank you.
Thank you. Okay, the next program is Outback Public City by Dr. Zhi Chen. Hello, Dr. Chen.
Hello, I'm online now.
Okay, I make some introduction. Dr. Chen. Dr. Chen Zhi received his bachelor's degree from National University of Singapore Engineering Science program with a specialization in optics and photonics. After graduation, he joined the research laboratory at Singapore MIT Alliance for Research and Technology. Since 2012, he began to pursue a PhD under the supervision of Professor George Barbastasis from MIT 3D Optical System Group. Dr. Chen's main research area is in 3D optical imaging system, holographic imaging system, computational imaging, and microscopy. Okay, welcome to Dr. Chen.
Okay, thank you for the introduction. My name is Chen Zhi, and I'm now the Vice President of OBEC. Today, I will bring a presentation about our company, OBEC. The title of the talk is A Visionary Revolution, 3D Sensing in Our Everyday Life. So I will introduce more about the applications and the commercialization of 3D sensing in our daily life. First of all, a very brief introduction about our company. Our company name is OBEC, and we are the world's leading AI and 3D sensing solution providers. We are based at Shenzhen city. We developed China's first 3D sensor chip, ASIC chip in 2015, and then followed by a 3D sensor cameras. So currently we have more than 800 patents in the field of 3D sensing, and we are also the Asia's first mass-produced consumer-grade 3D sensor manufacturers. Every year we ship more than a few millions of sets of 3D cameras to the world to use in different applications. And our clients include Ant Financial, Oppo, smartphone companies, computer company like HP and Bosch, and so on. So we were founded in 2013 at Shenzhen, and then we taped out our first chip in 2015, and then in 2016 we have our first generation of product used in television, PC, and robots. So in 2017 and 18 we commercialized the first the miniaturized 3D sensors that is used for the front-facing camera in a smartphone in Android market, and that is in the Oppo Find X. And in 2019 and 2020, we have a lot of new applications in the field of face recognition, payment, and a lot of things. And I will not spend too much time on this. I will briefly go through some of the most interesting applications that we might have already used or we have seen in our daily life. So currently 3D sensors, all this have been used in different fields like mobile terminals, like smartphones, and also smart retails that we can see in China. A lot of places are using the face to do the payment with Alipay. And then in the TV, in the service robots, and in a lot of other areas, people are using 3D sensing, and also like transportation. Just now, Dr. Charles from Waymo gave an interesting talk about how to use LiDARs, and this is also kind of 3D sensor technologies that's based on the direct ToF technology. So in the consumer electronics applications, we provide customized 3D modules and a service for smartphone, TV, and computer and pads, a lot of things. And we commercialized the world's first Android phone with Face ID features with a structured light 3D sensors in 2018. And in 2020, we commercialized this ToF technology, or more specifically, the indirect ToF technologies used in the Meizu smartphones in China. And also this year we commercialized the first first 3D cameras with a built-in 3D cameras in a TV to do this body detection, the gesture control, and AR gaming in a TV in a TV set. And also we have 3D Sync clone that we see in China and in the US. There are companies who use our devices to scan the room, to scan the house, and put this 3D models of this online so that people can have a virtual view of the house to do the house rental and house sales. Yeah. Okay, I think I will skip the video. And also there are some more precision measurement using 3D technologies, like for example, like this for the body scanning, foot scanning, face scanning, or some of the industrial parts scanning, like a bending tube scan. There are a lot of this kind of devices that we are making in our company in OBEC. So in OBEC, we design all these 3D sensors from scratch, from the very basic component level, like the VCSEL, the emitters, the receiver, even the sensor chip, and the signal processing algorithms, computational algorithms, and we design them into the ASIC chip, and then we have all those camera assembling production line. We do the calibrations and a lot of things, and also we are not just providing the hardware cameras to the market. We are also providing different kind of services like software, algorithm, or calibration services for the industry. So besides our business part, we have now have a lot of interesting things for the developer community, especially for the students and for those professionals who are working in these fields. We launched our 3D Vision developer community to provide a professional and effective service to all the developers. And the aim of this community is to help every 3D Vision developers. And this community platform will provide hardware, software, algorithm, SDK, and the other kind of technical support to make the 3D Vision or 3D cameras, 3D sensors easy to use. Or this hardware includes different kinds of 3D cameras, like the structured light cameras, the indirect ToF cameras, the LiDAR systems, and a lot of things. And we will help you to use this kind of sensors, and we provide these hardwares, and we hope we can help you to build your applications fast and success. And also, we organize a lot of community forum activities. We are now recruiting Android developers to do the administrations, and for these developer communities, there will be awards and different kinds of rewards for the top content contributors. And we also provide this kind of developer evaluation kit and for the faster development. And in our website and our WeChat account, we organize training courses. We will do this remotely online. We have different researchers from our companies or from the academy to do open courses about different applications, from the hardware level, from how to design the cameras or how to design 3D cameras, to the application level, like how to use this kind of data. So we have advanced course, like a real world advanced open course about the stereo vision, about the robotics. We also have basic courses about 3D vision, the introduction to different technologies. The instructors are from different fields. And we also have some casual workshops and discussions. And this is a schedule of our past activities and our future activities this year and the next year. Currently, we have already formed some alliance. Oh, wait, what is this? Currently, we have formed an alliance with a lot of third-party developer platforms like OpenCV and other like CSDN and this kind of platforms. Currently, we have some career opportunities. Sorry, my PowerPoint slides is just flashing. I think it has some automated play function. That's not the what I intend to do. Sorry about that. So currently we have some full-time opportunities about AI algorithms, optical engineers, IC design, software and hardware design. Our main location is at Shenzhen, but we also have offices in Shenzhen and Xi'an. If you are interested in this job opportunities, you are welcome to contact us via this email address, and also you can scan the QR code here to follow our account. We welcome students, the coming graduating students to apply. So thank you. That's all my presentation. I'm ready to answer some questions if you have.
Okay, thanks, Dr. Chen. Is there any question? Dr. Chen, I have a question.
Sure, yeah.
As you list, there are some different applications of 3D sensing. In your opinion, what application direction or what techniques of 3D sensing has more development prospects?
Are you asking the technology method that you think is the most promising, or are you asking which field of application is the most promising?
Both.
Okay, both. So currently, what we do is the mass production of or the mass application of 3D sensing technologies. So currently in consumer electronics, the smartphone industry is really a huge industry. Every smartphone's production is accounts for millions of sets. So I think smartphone industry is a very big industry for 3D sensing. And besides that, robotics also use a lot of 3D sensors. And another robotics includes those stationary robots and also those moving robots, and like those service robots. And up to a certain level, it will go to the automotive industry. So like the automotive driving cars and all the ADAS function, the ADAS sensors for the cars. So I think those are the huge industries that are using 3D sensors. And also for one application, not any specific field, but for application, the face recognition also use a lot of 3D sensors. They are used in different industry, like for payment or for the security and a lot of things. So these are the fields that are using a lot of 3D sensors. And about the technologies, about the technology methods, I think a lot of people are asking me these questions. People want to discuss this structured light, stereo cameras, stereo vision, indirect ToF or direct ToF, which are the best, which is the best solutions for 3D sensing. So my opinion is currently I don't see any of these solutions or any of this technology is superior than all the rest of the technologies. It really depends on the scene or the application you are using. Some requires very small footprint. You need a very small module. Some need a very, very long distance measurement, ranging abilities. So it really depends on the application. Different technologies have their advantages and disadvantages. So that's my opinion.
Okay, thank you. Is there any other question? Okay, no question. Okay, thanks to Dr. Chen's wonderful report again. Thank you very much.
Okay, thank you for organizing the activity, the conference. Yeah.
Okay, the morning's meeting is over, and the next is lunch break. Please note the meeting of the afternoon was start and 2 p.m. It is okay.
Yeah, thanks.
Yeah,
Go ahead.
yeah. Yeah, I was also muted. Yeah, so we see you again in the afternoon. See all the delegates.
Yeah, thanks, Professor Chen and Professor Liu for your great help.
Yeah.
Sorry, my poor English.
Okay. Yeah.
Okay, thanks, Dr. Jason Yuan and Charles Chi's great report. Thanks, Dr. Chen's share. Thanks everyone's listen. See you afternoon.
Okay, yeah. Thank you.
Okay,
Thank you, everybody.
see you.
Thank you. Bye-bye.
Bye.
Bye.